Arno Rauschenbaltel, that is going to be our first speaker, and he's going to talk about imaging and localizing individual atoms interface with the nanophotonic waveguide. So Arno, the floor is yours.
Thank you very much, Luis, and thank you also to all the organizers for inviting me. It's a great pleasure to give a talk at this conference, which should have been in Venaske, and seeing Lucas with his virtual background with this nice lecture hall in Venaske, I really have to say I hope that we will have the next meeting again in place. I'm really missing the nice atmosphere and the interaction with all the colleagues. So, as Luis said, I will be reporting on the imaging and localizing individual atoms which we trap near an optical nanofiber, and I would like to start by giving a short introduction because in recent years nanophotonic interfaces for cold atoms have been realized with various nanophotonic devices. It started out more than 10 years ago with our demonstration of trapping atoms near an optical nanofiber, but by now atoms have also been trapped and interfaced with one-dimensional photonic crystal cavities or one-dimensional photonic waveguides, and they have also been trapped in nanofiber-based cavities where you add resonant modes by inscribing mirrors into the tapered optical fiber here, or some kind of hybrid thing between these two, which is a nanofiber with a photonic cavity written onto the nanofiber itself. And all this research effort is motivated by the fact that such nanophotonic interfaces offer intriguing and unique opportunities. So first of all, the fact that we have a waveguide or waveguide cavity near our emitters allows us to engineer and also enhance the interaction between the atoms and the nanophotonic mode, because our nanophotonic device allows us to tailor the mode structure and in particular also introduce band gaps or resonances. And this then allows you to study the coupling of light and matter in an integrated setting where you also reach very unconventional parameter regimes, both in coupling strength and maybe also in the number of modes that you couple to. Then there is actually a peculiar property of such nanophotonic modes, which is that their polarization is linked to the direction of propagation. And that means that the interaction between the emitters and nanophotonic structures can depend on the propagation direction of light, which offers possibilities for protocols and applications. And taking advantage of all these assets, several building blocks have already been demonstrated for future quantum networks using such nanophotonic cold atom systems. So the experimental platform that we work with in our group is a so-called two-color nanofiber-based atom trap. So here we trap atoms using the evanescent field surrounding a sub-wavelength diameter optical fiber. And this evanescent field exerts a dipole force because it's far detuned. And we do actually send red and blue detuned light simultaneously through the waveguide. And the blue light will repel the atoms from the waveguide, while the red light will attract the atoms towards our nanofiber. And this fact, in combination with the stronger confinement of the blue light to the nanofiber, which means that an atom which approaches the nanofiber will first see the attractive red light and then the repulsive blue light, allows us to realize, combining the two light fields and choosing the detunings and powers appropriately, to combine the attractive force of the red and the repulsive force of the blue, such that we reach a minimum of potential energy for the atoms at a distance of 200 to 300 nanometers from the nanofiber surface. So this shows that it's possible to have stable radial confinement of the atoms, so as a function of distance from the nanofiber surface, but we can actually confine the atoms in all three spatial dimensions. Let us first consider the axial dimension, so along the nanofiber. In this case, we obtain confinement by using a standing wave for the attractive red light field here. So we are sending two counter-propagating red light fields into the fiber, and the resulting interference gives rise to maxima, so antinodes and nodes of the red field, meaning that along the fiber we now have a periodic potential where potential minima are separated by about half a micron in our case, which is half the wavelength of the red trapping light field in our nanofiber. So now in addition we can obtain azimuthal confinement, so around the nanofiber, and this is achieved by taking advantage of the dependence of the intensity of the evanescent light field outside of the nanofiber on the polarization of the light field. If you launch a linearly polarized light field into the nanofiber, then the evanescent field intensity in the plane of polarization is about 3 times higher than in the plane orthogonal to that direction. So if we now launch our two red and blue detuned trapping light fields such that they are orthogonally polarized, then we can have a situation where we have more attractive red detuned light field here and higher intensity of the repulsive blue detuned light field here, and thus we obtain also in the azimuthal direction a stable trapping minimum. So if I now sketch the resulting trapping potential in 3 dimensions, then we see that we obtain 2 linear arrays of trapping sites above and below the nanofiber. The distance from the nanofiber surface is about 270 nanometer in our case, and the trapping frequencies in all 3 spatial dimensions, so the mechanical resonance frequency of the atom trapped in this potential is about 100 kilohertz. And the atoms are localized in this trapping potential here in all 3 spatial dimensions to a volume much smaller than the wavelength. We load this nanofiber-based atom trap with cesium atoms, which are cooled with a magneto-optical trap using standard laser cooling. And when loading the atoms into this trap, we can reach filling factors of up to 50%, meaning that we have either one atom or no atom randomly in each of these potential wells. And there is an interesting effect which is referred to as the collisional blockade, which limits the number of atoms in these potential wells to 1. So we never have 2, thanks to light-induced collisions between the atoms. When 2 atoms are there, they just leave the trap. So while we were the first to demonstrate such a nanofiber-based atom trap, more groups worldwide have, still do, or will realize such nanofiber-based traps. And I hope that this list is not yet complete and that the community is still growing. Now, let me give one other part of introduction, which is on imaging and addressing single atoms in such light-induced potentials. So this has become possible about 20 years ago to image and address single atoms in optical tweezers and lattices, and has turned out to be an enabling technique for many exciting applications. from examining the dynamics of bosonic atoms in periodic light-induced potentials to preparing arrays of atoms in 2 dimensions and studying their tunneling dynamics and others, doing the same thing with fermionic atoms, and more recently having like perfect tweezer arrays filled with 1 atom for each tweezer by rearranging the tweezers after detecting whether an individual tweezer trap is filled with an atom or not. And this has even been extended to the possibility of realizing 3-dimensional arrays of atoms in arbitrary arrangements. Now, this opens a whole realm of possible applications and would, of course, also be desirable in such a nanophotonic cold atom systems as the one we are operating. However, in the case of nanophotonic cold atom systems, we actually face 2 major challenges when trying to image or address single atoms. So first of all, we actually are hampered by the scattering of the excitation light, which we use, or which we have to use to illuminate the atoms in order to image them, by the nearby nanophotonic structure. So since the atoms are scattering, resonantly scattering the light which is scattered off the waveguide or photonic crystal cavity will also contribute to the signal and may cover completely or impede the imaging of the atom. And then there is another effect which stems from Raman scattering of the trapping light fields in our waveguide material. So we use silica fibers, or you may use silicon nitride, for example, for photonic crystal cavities. But all these materials, when you send light through them, actually also exhibit inelastic scattering, Raman scattering, and this Raman scattering may produce a broadband background which can be near resonant with the excitation light, and which can thus not be easily filtered out in order to image the atoms. So when it comes to overcoming these challenges, there's some prior work already before ours, which was done. In particular, it was shown that you can image single trapped atoms which are placed in close vicinity of a nanophotonic circuit. However, in this work, the atoms were not yet coupled to the nanophotonic circuit, and imaging of atoms which were trapped in optical tweezer arrays were imaged about 3 micrometers away from a photonic crystal waveguide. In this case, obviously also not coupled to the waveguide, because the distance from the waveguide exceeded by far the decay length of the evanescent field surrounding the waveguide. And then recently, the fluorescence light of a single trapped atom, which was trapped near a nanofiber-based cavity, has been detected. However, here imaging was not performed, but it was the detection of the presence of the atom near the nanofiber using the fluorescence light. So maybe a few words on why it is hard, or what you have to do now in order to achieve single atom resolved detection. So we are facing in such systems 2 major noise sources. One is fundamental, it's Poissonian noise. So if you're detecting photons that come from a single atom, then there is the Poissonian noise, which is proportional to the square root of the number of detected photons. And then, of course, we are also facing technical noise, like, for example, the background that may stem from Raman scattering, as I mentioned. So while the technical noise typically will be some kind of offset, the Poissonian noise, of course, increases with the signal. However, it only increases like the square root of the signal, whereas the signal, which is the number of detected photons, of course, increases linearly. So this means that what we have to do now in order to image and detect single atoms is to decrease the background, so the technical noise here, and increase the signal, which means that we have to integrate for as long as possible, so have the atom available and scattering light for as long as possible, so as to increase the signal, right? Now, decreasing the background in our case was possible due to two tricks. First of all, we saw that by shifting the laser frequency of our trapping laser, it was possible to strongly reduce the Raman scattering background. So it turns out that the Raman shift, so the difference in frequency between the light field and the Raman background, is fixed. And so by suitably changing the trap laser frequency, we could reduce our Raman background by an order of magnitude. And then there was another technical issue, which is that for the cooling of atoms, you also need a so-called repumper laser. And formerly, this repumper laser was near the resonant frequency of our excitation light, but here we used the repumper on a different atomic transition so that the repumper could be easily filtered out. So then we are left with the challenge of keeping our atom for the longest possible time, so to take a nice picture of the atom with the largest possible number of photons. And for this, what we have to do, because when you're scattering light of the atoms, you usually, due to recoil of the photons, heat up the atoms. So we actually have to apply, while scattering light of the atoms, simultaneously cooling, so laser cooling of the atoms. And the technique that we used for performing this laser cooling of the atoms was so-called degenerate Raman cooling, which both cools the atoms and generates the signal. I cannot go into all the details here, but just briefly say that in this Raman cooling, we take advantage of the fact that the trapped atom in our trap features discrete vibrational levels, which come on top of each of the magnetic substates and electronic levels of the atom. And so by driving a cycling transition where you're scattering light without changing the vibrational state and then pump back to a state with one quantum of vibration less, you can actually continuously scatter light and still cool all 3 degrees of freedom, and use the scattered photons for imaging. And we actually, in another work, showed that this scheme allows you to perform near ground state cooling of the atoms in all 3 dimensions. So now all we need to do is to record this scattered fluorescence light of the atoms. And this is done with an imaging system. So we use an EMCCD camera that is capable of detecting single photons. And inside our vacuum chamber, where our cold atom experiment is operated, we have a microscope objective with a numerical aperture of about 0.3, which has a field of view of about 300 micrometers, and correspondingly point spread function, so the size, say, of our image that we can make with the microscope objective, which has a full width of maximum of about 10 micrometers. And then finally, we also use further bandpass and long pass filters to reduce the background of the light. And then when illuminating and scattering light off the atoms and recording the fluorescence of the atoms, we were indeed able to image single nanofiber trapped atoms. So here you see 3 CCD images recorded after half a second, after a second, and after 2 seconds after loading the trap. And you see that here we clearly discern 2 atoms trapped on our nanofiber, separated by a few 10 micrometers. After a while, the left atom is lost due to background gas collisions, and another second later, both atoms are gone. Okay, so let me stress that here we see a single cesium atom, which is at a distance of 200 to 300 nanometers from the nanofiber surface, so near some much larger device. And still it turns out that the atoms here are by far the strongest scatterer, which also tells you something about the flawlessness of such nanofiber, which is fabricated from standard optical glass fibers by flame heating and pulling. So we can now integrate the fluorescence detected in some 2D area region of interest here and plot the corresponding counts as a function of time. And then you see that we indeed have a clearly different level of counts depending on whether there is an atom or not. And here you see that the left atom was trapped for about half a second before being lost, while the right atom was trapped for about 1.5 seconds before being lost. And you also see that the integration time, so the rate at which we can take pictures and still nicely image the atoms, is about 200 milliseconds. And this is fast enough in view of the seconds that we can trap the atoms to really take live imagings, so movies of the atoms. So I don't know if Zoom allows me concerning the bandwidth to pass this image, but let me just show you such a movie of the atom. So here you see an atom trapped on the nanofiber, which then disappears. I don't know if you see it, so I let it run one more time. So you see the atom scattering light and then being lost. And we can take the same for 2 atoms here. So this is actually a movie where we see the right atom disappearing, and all these movies are in real time, right? So you see that we keep the atoms for a few seconds. So this shows that we can actually count the number of atoms which are trapped on our nanofiber, and thus for the first time this allows us to now perform experiments with a defined number of atoms, because formerly we were loading our trap in a random process where we transfer them from a magneto-optical trap and could only control the mean number of atoms, but not the precise number of atoms in a given experimental run. And one thing we then looked at to take advantage of this capability is the transmitted power of the light guided through the nanofiber and resonant with the atoms as a function of the number of atoms trapped on the nanofiber. And so here I show histograms of the SPCM counts, so of the single photon counting module counts, which count the number of photons that are transmitted through the fiber as a function of the number of atoms. And you see that the mean number of photons transmitted decreases as expected with the number of atoms. And if we plot now this mean transmitted photon flux as a function of number of atoms, then we see that we obtain indeed a nice exponential decay of the transmitted photon number. And you see that we have an optical depth per atom of about 4%. So about 4% of the photons are absorbed by each atom on our fiber. So if you wish, you can consider that this is an atom by atom test of the well-known Lambert-Beer law. Okay. So now let me come to a second experiment that we performed, taking advantage of our capability of not only knowing the number of atoms, but also knowing where they are. Okay, so here we looked at the interference of the light that is scattered off the atoms and then coupled into our nanophotonic waveguide. So we detect the fiber-coupled fluorescence with our single photon counting module, and we then post-select the SPCM data with respect to the atom number using the images that we can take and count the atoms, and then look at those runs where we had 2 atoms present. And then, of course, you expect interference between the light fields scattered by the 2 atoms into the waveguide, which depends on the separation between the atoms Z. So you have to take into consideration for finding the interference condition that you may have path length differences both outside of the fiber and in the fiber, and you find that this distance between the atoms times well, this wave number here, so a projection onto the 2 directions of incidence and nanofiber, has to be an integer multiple of 2 pi for obtaining constructive interference. So now, of course, the distance between the atoms is discrete in our case because the atoms are trapped in a periodic potential, and it turns out that the period of this trapping potential is larger than half the resonant wavelengths of the atoms. So while as a function of distance between the atoms you would now expect a nice interference signal with an interfringe distance of lambda here, we are only sampling this interference pattern at discrete points, which are separated by slightly more than half the resonant wavelength. And so as a function of the atom separation in units of lattice spacing, we expect such a sinusoidal signal which varies with a lower spatial period, right? So the first thing we looked at now is simply the SPCM data here without atoms, with 1 atom, and with 2 atoms, irrespectively of the distance between the 2 atoms. And you will see that we can already learn something from this measurement. So I show you here the histogram of our detector counts for 0 atoms, and you see that we have a background for 0 atoms around some mean value of 300 SPCM counts, and then if there is an atom, you see that the histogram is shifted to higher counts. But then when we look at the photon count distribution for 2 atoms, this photon count distribution differs qualitatively from the 1 atom case. And this shows, and is of course also expected, because the scattering of the excitation light by the atoms is mainly coherent. And so you would expect that the histogram ranges now from the 0 atom value to the 4 atom value when constructive interference takes place, where 0 atom value would be for destructive interference, right? So this, while the scattering of excitation light by the atoms is mainly coherent, my computer is somewhat slowing down. Right now it doesn't move. Do you still hear me?
Yeah, we hear you. And
yeah, now it works again. It was stalled. Thanks. Actually, it turns out that what we observe is not an incoherent sum of the fields, which would be this green dashed line here. It's not a perfectly coherent sum of the fields, which would correspond to this red dashed line here, but it actually something in between with about 29% of incoherent scattering. And for reasons of time, I will not go into the details. You can ask me why we have some incoherent scattering here. I just want to really convince you that there is also coherence in the scattering. So let us examine the dependence now of the SPCM counts on the atom distance. Remember that you expect some sinusoidal variation of the scattered power as a function of atom separation in units of lattice spacing. And indeed, when we determine the atom separation by performing point spread function analysis and measuring the position of the atoms from our images, and then performing a Fourier transform of the corresponding interference signal, we see that there is a predominant spatial modulation with a period of 3.7 micrometers, which is in good agreement with our expectation of undersampling the interference pattern. So with this, let me summarize. We demonstrated here the capability of performing, localizing and imaging single nanofiber trapped atoms in situ, so while they are trapped. This significantly enriches, in our view, the experimental toolbox for nanophotonic cold atom systems. And to show this, we performed two experiments, one where we did a number-resolved test of Baire-Lambert law, and then we also studied the collective scattering of light by two atoms on our nanofiber and showed that there's interference between the scattered fields. Now, where will all this lead to? First, I think that these results give an excellent basis for studies of collective and waveguide mediated effects in nanophotonic systems. In particular, we may be able to study sub and super radiance while exactly knowing the number of waveguide coupled atoms. We can investigate spatially resolved self-organization of quantum emitters along the waveguides, possibly due to smartly designed novel optical forces. And in general, this work shows that we can now implement position-resolved real-time feedback and also step-by-step assembly, as has been shown with free-space optical tweezers, but in the setting of cold atom-based nanophotonic quantum devices. With this, I would like to thank the co-workers that really did the work. As I said, I hope the pandemic will be over soon and we meet again in Benasque in 2 years. I thank the funding agencies and I thank you for your attention.
Well, thank you very much, Arno, for this amazing talk, and we really hope that you will have a follow-up in 2 years' time, but live in Benasque. So now there are some questions posed by the audience. So the first one is by Carlos Gonzalez that says, very nice talk. Is it possible to bend the nanofibers in order to generate a kind of feedback interaction with the atoms?
So is it possible to do what with the nanofiber?
To bend the nanofiber.
Okay. So, well, let's say in general, it has been shown by other groups. We always only work with very straight nanofibers, but it has been shown that you can make not resonators and really make like loops out of nanofibers. Combining this, so while this is a photonic device which then has resonances, combining this with trapping atoms, however, will be challenging because then you have to deal with the fact that also your trapping light fields will see some resonant mode structure and will suffer from incoupling variations also. So I think it will be very challenging to have these nanofiber-based traps in bent waveguides.
Okay, there is another question by Sebastian Slama that says that whether you could image also atoms in the two traps opposite of the fiber.
It's a very good question. So actually in the work here, one thing I did not go into detail was the degenerate Raman cooling, and it turns out that this degenerate Raman cooling only cools atoms on one side of the fiber and it heats atoms on the other side of the fiber. So here in this work, we dealt only with one array of atoms trapped along the nanofiber, and the other one was absent, and we were imaging from the side where, from the atom side. So we never tried to see, but it would be worthwhile checking whether we can see atoms behind the nanofiber, but here we only work with atoms in front of the nanofiber.
Okay, so I think in the interest of time, we have to move on with the next talk, but there is another question that is a bit more technical, so maybe Arno, you can answer it by the chat.
Yes.
Okay, thanks a lot. Okay.
Thank you very much.
So before that, let me put this research a little bit into the context of quantum technologies, or the use of light-matter interaction in quantum technologies. So by now, actually, after this whole week, we have seen that the interaction between light and matter can be instrumental for many applications, ranging from sensing, metrology, quantum networks. And the one that will be more specific to this talk is about the possibility of mediating interaction between localized emitters or qubits that eventually can be harnessed for developing quantum gates for quantum computation, but also for quantum simulation applications. So this will be what this talk will mainly focus about. One has to say that already in free space, you can mediate interaction between quantum emitters. So an emitter can be excited, emit a photon, and be absorbed by the other atom, and this will lead to some unitary evolution between them, some coherent unitary evolution. The problem is that in free space, you have limited tunability. So the range and the strength is kind of limited. For example, because the photons has to be propagating in the whole three-dimensional space, so they will eventually decay very fast. So these interactions that appear decay very fast with the distance. And also, typically, they are accompanied by some non-unitary dynamics induced by the dissipation. So, eventually, this photon can be lost somewhere else, and this can give rise to what I write here, both individual but also collective dissipative terms. So, typically, it's very difficult to exploit these free space photon-mediated interactions. There are, of course, certain ways that people have been thinking about going beyond these limitations, either by building cavities or through tight focusing, also exciting atoms into a highly excited state using Rydberg atoms. But I would say that still there is room for improving the tunability, especially of this free space photon-mediated interaction. And this is where I think this quantum nanophotonics, which is the topic of this platform, can be very, very useful. So actually, in the last few years, I've been working a lot about basically how to exploit this hybrid system where you put well, like the one presented by Arno, for example, where you put atoms close to these nanophotonic structures. So we wrote this review here about this topic, and actually, well, Arno presented it very well. So there are many experiments ongoing already. So it's a very active topic of research. But actually, I also want to point out that, this framework where you have kind of localized excitations that interact with a continuum of modes that are propagating a low-dimensional field is now can be exported also to other frameworks, and in particular, so there is a lot of now experiments also with circuit QED, where they try to mimic this physics with microwave resonators, a couple of microwave resonators, also with phonons, and even simulate this light-matter interaction with matter waves. That's something that was discussed a little bit by Ignacio Cirac in the first talk of the workshop. So, there is plenty of room for that this research on quantum optics in low dimension can be applied, basically. So the reasons why this nanophotonics is particularly appealing for this purpose of mediating photon interactions is, well, this has been mentioned several times during this workshop, but the fact that the light can be confined in this structure to a subwavelength scale naturally enhances light-matter interactions. Also, quite important is the fact that the light, because it propagates into a low-dimensional field, typically the interaction ranges increases because the light doesn't have to be spread into the whole solid angle. But also, and last but not least, the possibility of patterning this structure by designing different holes or putting different geometries basically allow you to tune the band structure. And as Arno was pointing, so you can change the propagation of the photons by this change of band structures, and this will eventually translate into different type of atom-atom interactions, actually. So this is a little bit actually the things that I want to exploit, these effects that I want to exploit for this talk. and in particular explain the fact when this band structure has certain topology, non-trivial topology. Just to introduce a little bit the field, so the field of topological photonics started a few years ago with this paper by Haldane, where they realized basically that it was possible to obtain also topological effects with photons. And in particular, I mean, this triggered a whole new field, a new avenue in photonics, and it has been very popular. There has been many realizations in many different platforms that I list here a few of them. I recommend this review where there is a very good review of the state of the art of the field. And the main focus in this field has been so far exploiting what I would call the linear regime. So basically trying to excite the edge states, the non-trivial edge states that appear in these systems to be able to design unidirectional flows of light that are also robust to disorder, no? So that you can have defects and this flow can still go on without the scattering. However, as it was also pointed in this review, one of the next frontiers of the field is actually to study this interplay with quantum emitters. In my view, this is very interesting because these quantum emitters are highly nonlinear systems, and they can somehow go to translate, basically when you couple them to these topological photonic systems, you can induce some kind of interaction in these photons and possibly explore this highly non-trivial interacting topological photonics regime that is not so easy with purely photonic systems. And in fact, there has been already some experiments. So I put here like this experiment by Hafesi and Edo Watts, where they were coupling to a photonic crystal to the edge modes of this topological and non-trivial photonic crystal, and a more recent one by the group of Oscar Painter done with microwave resonators that I will talk a little bit more afterwards. So this is basically what this talk will be about. So it's about what kind of new quantum optical phenomena, in particular, what kind of new photon-mediated interactions appear when you have these topological photonic bandgaps. So in these topological photonic systems, you typically get photonic bandgap structures. So you have regions of energy where the photons cannot propagate. I will explain first what happened with the kind of conventional bandgaps to then make a difference with what happens with our topologically non-trivial systems. And in particular, I want to talk about two works, one with the photonic SSH model that I did in collaboration with Miguel Bello, who is now in the group of Ignacio, Gloria Platero, and Ignacio Cirac. And another line of research that I've been following, which is what happens with three-dimensional reservoir, in particular, when they have this topological biophotonic structure. Okay, so I mean, this field of the study of light matter interactions in photonic bandgaps was started more or less in the 90s. There are some older papers, but I think that could be a good starting point. And what they realize is that actually if you put an emitter, which is tuned with the optical transition tuned to the bandgap, so the emitter, instead of displaying the typical fraction, I mean, the typical exponential decay, so you see that you basically have this fractional decay, so that the spontaneous emission becomes quenched. And the reason why this is happening is because the photon that should be supposed to be propagating, so it cannot propagate far away from the emitter, and eventually forms what is called an atom-photon bound state. This is quite very interesting. Let's say with a single atom is maybe not so interesting, but when you put many of them, this is very appealing because actually you can realize that if actually you trace out the effect of the photons and you see what happens with the effective dynamics of the emitter, so the emitters can basically talk through this bound state physics and mediate purely coherent interactions between the emitter. So actually you get rid of the non-unitary part mediated by the photons in this bath, and you end up with a purely coherent evolution, coherent exchange between the photons. And this is nice because also this interaction is tunable in the sense that actually the length of this bound state, you can tune it with the tuning of the optical transition with respect to the band edge actually. So this is pretty nice. But what I've been thinking, like after this paper, of this 2015 paper, I was thinking of going beyond this simple paradigm. And one of them was basically to couple to this topological photonics environment. So let's see with the most simple example, this one-dimensional model, which is this photonic analog of the SSH model. This is a very simple model. That is the one probably most studied in topology because it's super simple. It's just in the photonic framework, it will be a set of coupled cavity arrays, a tight binding model, but what the tunnelings are basically a stagger in the sense that then you have a parameter delta that controls whether the AV or the VA couplings are larger or smaller. And basically, when this small delta, of course, if it's 0, you recover the standard tight binding. But when it's different from 0, what happens is that you have two bands that are symmetric with respect to the center. It has some chiral symmetry. And basically, you have a middle band gap and an upper and a lower band gap. And the key point is that actually you can define an invariant, so that basically when this invariant is different from 0, so you basically in an open boundary condition system, so in a finite system, you will have edge modes or not that have this kind of topological origin. In our case, actually, we are not interested in coupling the emitters to the edge modes. Actually, what we are interested is to ask ourselves, if you were, for example, to put an emitter in the middle of one of these chain and very far from the edges, will you be able to still sensitive to some kind of the topology of the band? And this is the kind of thing that that we are wondering. So what I will do now is actually do this kind of Gedanken experiment. So I put an emitter in one of the center, and I calculate what will be the bound state shape, so the photonic wave function, as I tune the energy of the emitters into the different bands, into the different band gaps of this model. So you see that you have here, you can be below this band, in the middle band gap, or in the upper band gap. So if I put the emitter in the lower band gap, so I put the energy of the emitter here, and you calculate the photonic wave function associated to this bound state, what you see is that actually the bound state is basically exponentially localized. It very much resembles the one of the standard bound state physics, or the standard waveguides. So here the different colors are the different weight in the different sublattice, and 0, of course, is the place where the emitter is. If you are in the upper corners, also you have some exponential localization. The only thing you get is some alternating sign in the different sublattice. But this is also something that happens in the standard tight binding model. So it's nothing very particular here of the topology. However, when you are exactly in the middle, this is something more kind of striking. And in particular is that you see that the emitter is only localized to the left, actually, well, here to the right, or to the left, depending on the topological phase, or depending on the sublattice that you are actually coupling. And this will be kind of the chiral bound states that we call it. And actually it has a topological origin, because actually what is happening is that when you are putting the emitter in the middle, so that you are dividing this infinite chain in two semi-infinite chains, and one of them will have a topologically non-trivial, well, basically it will have edge states, and this will be the edge state that will couple the emitter and form this atom photon bound state. So actually, if you want to know more about this origin, there is also some nice follow-up paper about the group of Ciccarello, where they also explain this topological origin of this kind of bound states. But these are pretty nice, because now actually, well, first is that after our paper, so we were approached by the group of Oscar Painter, and they were actually be able to measure these bound states. So they were building this tight binding chain just with basically LC resonators, a set of LC resonators, microwave resonators. And through photon scattering, they were able to prove actually the character of this bound state and whether they were coupling to the left or to the right. And they were able basically to explore these properties that I was mentioned before. So it's actually pretty nice. So one nice thing also of these bound states is that they inherit some robustness to disorder due to the topological origin of this bound state. So here what we do, for example, is that actually we compare the result of the bound state here in the upper, middle, and lower band gap without disorder. And then here comparing with the case of where we add some off-diagonal disorder. So it will be disorder in the tunnelings. And you see that, for example, the bound state in the middle, basically the energy does not change, remain P not 0. And actually the wave function also is not changing, while the other ones are basically affected. And although basically when you add diagonal disorder in the energies, because this basically does not respect the symmetry that gives rise to the topology in this model, so they become a little bit affected, but actually you can also show that they are more robust than the upper and the lower band gap bound state modes. So actually this is also some nice property. So what is nice is that this is not only a single emitter feature, but now when you go to many, of course, the interactions that I was mentioning that appear when you have many emitters inherit the shape of the bound states. So in particular, see here we plot the weight of these dipole-dipole couplings as a function of this small delta parameter at a fixed distances. And there you see that depending on the delta sign of delta, they will be able to talk. It will be 0 or non-zero. Of course, this interaction will be kind of the coherence free. So if you put an excitation in one emitter, so you will have perfect coherent exchange between the emitters. And And also what happens is that if you put not two, but you put many, and you calculate, for example, the ground state of these phases, you'll see that they will stabilize many body phases with different magnetic orderings. So here I don't want to enter into a detail, but just to say that, well, I mean, just because of the peculiar shape of this interaction, that there will be long range and with some alternating signs, you have here some double nil ordering of the ground state compared to the simple nil order in the other case. But there is a lot of details here. Unfortunately, I don't have the time to go to them. Because I wanted to talk a little bit about this biophotonics. So these biophotos, in case you are not familiar, so a biophoton, I mean, this occurs basically when you have two linearly dispersive bands that are touching at single points, at the generate points. So they occur in three-dimensional baths when you break either inversion or time reversal symmetry. And they have already been measured experimentally, so actually in photonics. But actually what we took for our calculations was a discrete model based on some proposal with ultra-cold atoms, actually, where they break a stagger, basically the inversion symmetry by using some stagger hoppings. And we also have some tunable parameters, some stagger mass parameters, so that we can control the position of these bile points, actually. So what is characteristic of these bile points? So the thing is that they are, well, basically, I mean, when you have them, you have bile points. So you can calculate the Berry curvature associated to these bile points. And actually, you can see that they are sources of this Berry curvature. And you have basically two of them with opposite chirality. And the nice thing of these bile points is that, I mean, you can move them, and through this parameter M that I was showing you before, you can move the position of these bile points, but they basically only are annihilated when two of them of opposite chirality meet in the Brillouin zone. And this, for example, this movement can be triggered by this stagger mass parameter that I was mentioning before. But the nice thing is that in spite of this movement, if you calculate the density of states, you see that, well, independent of this mass, as long as this mass is smaller than 2J, you see that the singular bandgap nature that appears here, like in the 2D two-dimensional Dirac point, remains there independent of this mass. Basically, I mean, the important thing is that you will be able to have a singular bandgap by changing the band structure in the middle. And now, of course, the Gedanken experiment is what happens now if I put an emitter tune to this particular singular bandgap region. And what happens is that you also get a kind of a localized mode, but differently from the kind of SSH or the conventional bandgaps. Now this bound state is localized with a power law shape. So this is, I mean, here this is the three-dimensional projection, and here we make several cuts, and they are localized with a 1/d square law. And the nice thing is that also through this topological protection, this is just to say that this is something similar happens in two-dimensional Dirac points. But the difference here is that now through this tunability, so through the fact that I can move the bile points without opening a bandgap, so I can change the nature of this power law hopping, but without getting this exponential attenuation. So I can have some tunability of the power law. They also inherit certain robustness to disorder. So the power law, if you make several realizations and you add disorder in the energies, so you keep this power law nature. And of course, if you put not one, but several emitters, you will be able to mediate this tunable, I mean, this perfect coherent exchange oscillations between them, actually. So they are really a way of mediating long range, the coherence-free and robust to disorder interactions. So with that, let me wrap up and leave some time for questions. So I hope to have convinced you that, I mean, this interplay of quantum emitters or quantum optics and topological photonics can give rise to interesting physics. So I have shown you in particular that, for example, it gives rise to novel spin-spin interactions in 1 dimension and 3 dimensions. I put here the 2D because actually I think the next talk by Daniele de Bernardis will be actually about a 2-dimensional setup explaining these things. And also, once you have this novel spin-spin interaction, so I mean, you can have some novel phenomenology. Like I talk a little bit about the fact that you have these novel many-body phases that, I mean, you can find them better characterized in the paper, but and also do some long-distance quantum gates. You can think of them as a way of doing these things. And with that, just I wanted to acknowledge again my collaborators, well, especially Miguel Bello, who did most of the first part of the work, and Iñaki García-Elcano, who did also most part of these biophotonic environments. And with that, I thank you also again for your attention.
Okay, thank you very much, Alejandro. We have a question now by Carlos Gonzalez that says, thank you very much for the nice talk. Can one obtain topological behavior by staggering the eigenenergies of the nodes? For instance, the cavity frequencies of the SSH model instead of the hopping rates?
No, actually, you can see that this does not give rise to a topologically non-trivial phase. No, this is you open a bandgap, but you open a trivial bandgap. Let's say.
Although you can do both.
You can do both, but then you lose some of the properties of this. You lose the protection because also, I mean, the problem is that if you stagger the energies, you are losing the chiral symmetry that is giving rise to the non-trivial topology of the SSH. You can do both for example, in the bile photonics, this is not so critical because you can have both, let's say. I mean, if you stagger this mass up to some point, you can still have this kind of power law interactions.
Okay, there is another question by Luis Rax that says, thanks for the talks. Is it possible to tune the Weyl point power law decays to exponents other than integer multiples of 1/2? Additionally, how would such a lattice model be implemented physically? Well, to the first question, I think I don't know if you have seen, but in the middle of, I mean, so here I was putting just some values of the M value in the middle. So you are also implementing kind of different power law exponents. So you have kind of some continuous tunability of the power law up to a certain extent, I mean, for this particular model. So I'm also working, I mean, I'm a bit obsessed with this power law interaction. So I'm working on ways of actually further tuning it. Regarding the experimental implementation, the way they do it, they propose in this cold atom setup, basically is that they start by this, the way that they simulate this Harper-Hofstadter model, that is a two-dimensional array with some complex phases. And then they add the third dimension by adding some other optical potential in the third direction to induce this stagger hopping as well. So this would be the way with kind of matter wave proposals. And in photonics, it's much more complicated. You have to find ways of breaking this inversion symmetry. So I think that qualitatively you will find similar physics, but you know, it's more challenging. Yeah. Okay. Yeah, I have another question: is whether this power law is peculiar of these Weyl points, or maybe you can.
As I said, in the two-dimensional Dirac points, you also get a power law. And you also have some tunability if you add anisotropy. But the thing is that for example, if you add a stagger energies, so you open a bandgap, so you trivially go to exponential. So so basically, I think it's typical of singular bandgap. So when you don't have a bandgap of a single point, no, like in Dirac points, Weyl. Also in diamond lattice in 3D, you also have a singular bandgap. So you also have power laws. So I mean, the key point is that somehow you think that the band structure doesn't have a mass. No? I mean, so the photons do not have a mass, so that they are linearly dispersive at the point. Okay. Well, there are no more questions. Thanks a lot, Alejandro. And we'll move to the next talk. That is by Daniele De Bernardis, and he's going to talk about light-matter interaction with synthetic magnetic fields, Landau-level polaritons.
So yeah, thank you a lot for the introduction. Can you? Okay. So yeah, everything's fine here. Can you hear me? And okay.
Yeah, everything is fine.
Okay, good. So yeah, thank you a lot for giving me this opportunity of participating to this talk. And so I want to start, okay, my talk is like, as Alejandro already introduced, basically is like a continuation of his work, but in a two-dimensional system. And I want to thank also my collaborators, like first of all, Peter Rabel, which is my PhD advisor, and Mohamed Hafezi, so in which I actually started with this project, and together with Zipei-chan, which is his postdoc, and also with Jacopo Carusotto in Trento. And you can find it on the archive, and it will be soon on PRL. So the context was already introduced by the very nice talk of Alejandro, which is basically an overlap between quantum nanophotonics, like light matter interaction in nanophotonic lattices, and topological photonics. So, and the idea is like to put these two things together in order to have light matter interaction, but with a photon which has a non-trivial topology. So in our work, we actually considered like one of the simplest system that you can find, which has non-trivial topology. Probably the simplest one is what Alejandro introduced, this SSH model. And the probably second simplest one is the two-dimensional lattice in which we have some complex hopping. So each of these lattice size, you can think it as a resonator in which we have a photon. The photon can hop between different lattice sizes with nearest neighbor hopping, but the hopping has a complex phase. And this is actually very interesting because you can eventually tailor this phase in such a way that you will mimic the effect of a magnetic field which is coupled to the photon. In our work, in particular, we considered homogeneous magnetic field, which is basically controlled by this parameter here, alpha, which represent the flux, the magnetic flux into a single plaquette here. And this system is well known. So this system is well known since the 60s, the 70s, probably in the context of electron in materials. Then it was used again in the context of quantum Hall effect in materials. And then it was like people started to use it with bosonic degrees of freedom to describe also like setups with like optical photons, like in Mohammed's group, or in Jonathan Simon's group with superconducting circuits. So now the question is like, what happens when we couple atoms or artificial atoms, in general emitters, two-level emitters, to this magnetic photon? And I want to really start with the very basics here. So you can think, so you have this photon that lives in this two-dimensional lattice, and we can actually think this photon as like in a classical way, it's a particle going around. And now we turn on a magnetic field, and this photon kind of feels this magnetic field, this artificial magnetic field. What happens to a particle that feels a magnetic field will start to go on a circular trajectory. So it doesn't propagate through straight lines, but it starts to propagate through circular trajectories. So now you can think a simple Gedanken experiment in which you load one excitation in your atom and you let your atom emit in your lattice. Without magnetic field, if we don't consider like very special kind of pathological features, normally the atom will just emit and the photon will just escape toward infinity. And we can picture, have in mind, very end wavy, what happens here is like the photon will just goes away into straight lines, like light rays, in all directions far away from the atom. Now we turn on the magnetic field, and we must think these straight lines are turned and are bent into circular trajectories here. So what happens, like the photon actually cannot really escape, because once the photon is emitted, it goes on these circular trajectories, and then it will come back on the atom. So, and eventually you really get stuck on a kind of cyclotron orbit. And this actually, if you think about it, is really the definition of what is like a bound state. So we have a bound state between the atom and the photon, and the peculiar feature of this bound state, which is induced by this synthetic magnetic field. I have to, like, I put here these two papers among all, like there are really thousands of papers about this topic of atom-photon bound state, but I want to highlight inspirations because working in the group of Peter Rabel, I got in touch with Giuseppe, then I started to read this paper, and And when I was in Maryland with Mohammed, I just put them together, and that was the result. So now we can confirm this and wavy idea just simply implementing it on a computer, and it is kind of simple. So we just implement this Hamiltonian. We have a single atom which is coupled in the center, for instance, of this two-dimensional photonic lattice. We load one excitation into the atom. We let the atom emit, and okay, here I put the spectrum of my two-dimensional photonic lattice. This blue line is the spectrum, fairly continuous and fairly linear. And this would be like the frequency of my emitter. I let the emitter evolve, and it will just decay kind of exponentially, just spontaneous emission. Now I turn on the magnetic field, and what's going on is like I start to see these Rabi oscillations. Why? Because, okay, I need to take a look to this spectrum here, and now the spectrum of the photonic lattice, it gets organized in some bands which are quite degenerate, let's say. And now my atom is in resonance, for instance, with this band here. And being in resonance with this band, it will give rise to these Rabi oscillations, in which this Rabi frequency, which determines the Rabi splitting of the bound state, actually it scales with the magnetic flux. Then, okay, one can ask what happens if I am in the band gap. Actually, nothing happens. So the atom simply doesn't evolve at all. There are no states available to do any evolution. So really, what the main physics of this single atom, single photon in this photonic lattice is basically to form these bound states. And what happens if I look a bit more into the origin of this bound state? In particular, I take a look to the photonic wave function. So I just look at the photonic density when I'm in the minimum of these Rabi oscillations, and they look kind of like this. So the shape of this photonic density, of the photonic wave function of this bound state, depends from the resonant condition. So this holds for this zero band, this for the first band, second band. And the kind of interesting feature here is like we have a chirality, which is intrinsic in this bound state. And this chirality, one can see it by calculating the current, the photon current. And then you can understand that this photon is actually not at rest, but is circulating in a particular direction. So this is a chiral bound state, but not only chiral, also it will break time reversal symmetry. So now I want to go a little bit on the technical side of this story, because actually so why we choose this system? Because it's the simplest basically, but also because really you can actually solve it almost completely. And this will give rise to, I mean, it's a kind of paradigm, okay, it's a kind of paradigm for this kind of system in which you have photons and magnetic fields, and also to understand, hopefully, other topological systems, let's say. So, okay, here let's go back on this photonic lattice with this complex phase, with this homogeneous synthetic magnetic field. I plot again the spectrum here of the photonic lattice, but now in function of the magnetic phase. And the result is this particular plot here, which is well known in the literature as the Hofstadter butterfly. And this plot here, this spectrum is characterized by the fact of having these bands. So the spectrum is organized in bands, which are separated by band gaps. And there are these very kind of beautiful fractal structures all over the place. Well, okay, people know almost everything about this Hofstadter butterfly, but what I want to show here is a particular perspective. We can actually take a logarithmic scale of this plot here, nothing fancy, and we can take a closer inspection. And we can see that we can actually identify 3 regions here. One region, we have kind of continuums of modes. One region, we have these bands which are very well separated between each other by spectral gaps. And one region in which all these fractal structures are dominant. And here, of course, is the magnetic field strength, basically. And we can understand these 3 regions by introducing the so-called magnetic length scale, which is well known, like for people that does this quantum Hall effect and all these things knows it very well. And if we compare this quantum, this magnetic length scale, now can be compared to the main length scale in the game, which are the size of the system, if the system has finite size, and eventually the lattice spacing in the systems, because this is a lattice. And we can see that, okay, in one limit, we have actually the magnetic length is much larger than the system size. And here there is this continuum. Why there is this continuum? Because you can think it very like in a very end-wavy way, like this length scale give this magnetic length. It gives basically the minimum cyclotron orbit that the system will support. And this minimum cyclotron orbit cannot really fit the system. So in this system, the magnetic effects are actually just perturbative. Then the opposite limit is like this magnetic length is very small. So magnetic effects are absolutely non-perturbative. But on the other side, it's so small that is in competition with the lattice spacing. And here you get all these crazy fractal patterns. And then you have this length scale in between, in which the magnetic length is actually much larger than the lattice spacing and is actually smaller than the lattice size. And here in this kind of region here, we can actually take a continuum approximation, and we can consider this band as basically the Landau levels, which are very known in standard quantum mechanics. And these actually open up a huge variety of opportunities. Why? Because once you know that once you are aware of this approximation, then you can solve what is called the Green function of the photons. And the Green function, also called the photonic propagator, tells you basically everything about the photons property of the system and will allow you to solve all kind of possible situation of light-matter interaction with very reduced complexity. So to know the Green function here, which is the the photon two-point correlator, we need to know this mode function of the Hopling matrix. But now we have seen, okay, I take a rather moderate magnetic field, which is actually really available in current experiments, and I approximate the lowest part of the spectrum as Landau levels, so degenerate levels, equispaced, and I know this Landau wave function from standard quantum mechanics. I wrap up everything together and I get a nice closed expression for this Green function. So now I don't want to enter in the detailed mathematical details here, but this Green function has various properties, and you can really write it down everything in a kind of simple way. So now you can actually use this Green function to build up more complicated situations in which you have more photons, more atoms. Because now the situation is interesting. So this system is kind of now very, let's say, we can really understand now what's going on here. So we have this atom. Around each atom, there is a cloud, an orbital, a Landau orbital. And if I eventually take two atoms, when they are far apart, nothing really happens. But when their distance is similar to this magnetic length, then this orbital will start to play together and overlap. And this is actually the case. If I take some simulation, then I can see that. So this is the energy spectrum. So I have two degenerate levels when they are far apart, and nothing really happens. But when the atoms, they get close together, they start to hybridize the orbitals and to share their photon in this hybridized orbital, and they start to form basically a new bound state between the atoms. And so basically there is a real covalent bonding between these magnetic, these polaritons, and they will give rise to basically these magnetic molecules, as we want to call them. So now we can use this Grimm function, as I said, to make this, to develop really the formalism in a very rigorous way, and basically to write down like an effective theory that describes the situation of many atoms interacting just with one of these single bands. And then we can define new local degrees of freedom for the photon, which basically this would be an annihilation operator of a photon in a Landau orbital here. And in this way, we can rewrite a new Hamiltonian, and we can throw away all the rest of degrees of freedom in the lattice and really have a huge numerical simplification. With this, we can study, for instance, the case of many atoms, multiple atoms case in function of their relative distance. And if we plot the spectrum, for instance, we'll get these fractal patterns that you will see in the Hofstadter butterfly. But now with the difference that these patterns here will arise because of the interaction between all these Landau polaritons, to say. And the other interesting case is like if we consider many atoms, but also with many photons. And here we can start really to enter in the regime of having a quantum simulator of fractional quantum Hall physics, but with photons, because what's going on here is like, if I have two photons, then I realize that I create a system in which this is the spectrum of the system, the spectrum with one photon and with two photons. And if I look at the lowest states in the two photon spectrum, I see that those states here are states in which the photons, they will avoid each other, like Laughling-like state. And okay, this is the photon density, and this is the two photon correlation function seen by this atom here. And this means that basically for all these states here, the two photons, they will, if there is a photon here, the other photon must be either here or here, but there are never two photons here. And that very interesting, the fact that when you go to very small scale, all the atoms, they will basically fall in the same orbital. And being in the same orbital, you realize basically cavity quantum electrodynamics, but with these Landau orbitals, so they will interact just with a single orbital. Then let me close my talk here with just, so far everything was in the assumption that we are resonant with one of these Landau bands, but now we can say also, like as Alejandro also anticipated in his talk, it's very interesting also to look at when the atoms are in a band gap, because you can eventually, if there is just one atom, in this case nothing really happens, but if there are many atoms, you can actually eliminate the photonic degrees of freedom, and this will give rise to effective atom-atom interaction. And this is a very special type because it will have like a non-trivial Aranon bomb phase here that you will get from the lattice. And it will have like very interesting properties of long-range interaction that depends on the resonant condition here. Depending on the frequency of my atoms, I can actually make this interaction short, very short range, or even very long range. And again, I can actually see this kind of chiral dynamics. To mention again, this kind of interaction can be tailored also to mimic this Kapit-Muller interaction here, which are very, like it's basically a toy model to study fractional quantum Hall states. So this is really another way to simulate fractional quantum Hall type of physics. And with this, I'm done. Yeah, so this is my last slide. Yes. So open for a question now.
Okay, thank you very much, Daniele. There's one question by Alejandro actually that says that very nice and clear talk. What is the asymptotic spatial decay of these states?
So these states here, for instance, here we see an example of the photonic density. So they scale like a Gaussian. They have a Gaussian envelope, which is multiplied by a Laguerre polynomials. So they really scales like hydrogen atoms orbitals, basically.
Okay, I have a question myself. Is you talk all the time about the bulk properties. Have you considered a finite system, and do you have edge modes, and do you have?
Yes. So actually, this because of the timing, I just skipped to say it. But so, for instance, in this picture, this has finite size, okay? But the thing is, like, what I plot here is the local density of state, which is seen by the atom, and my atom is in the middle of the system, near to the center, and the edge states are exponentially localized on the edge of the system. So you actually don't see the edge state. But like Jonathan Simon, for instance, now is looking for this kind of physics, but on the edge. But it's completely different. So you will get completely different physics there. You don't get this bound state on the edge.
Okay. We have another question by Javier Del Pino that says that it's a beautiful talk. Is there any particular happening with the bound states when the Hofstadter spectrum has a finite number of bands? In particular, I mean the cases where magnetic field and lattice lengths are commensurable.
So, so you mean like if you are in this region here, or? Because okay, so what I presented here is basically everything about this region here. Once you go here, no, the situation becomes a bit more unclear. It's not so easy to see what happens. So in general, you can think that here the bands, these bands that here are basically degenerate. Here they have a certain width. So you will actually have a kind of spontaneous emission, but with complicated dynamics, and these bound states are not really true anymore in this region here. So you really need to stick to this region here to see these bound states.
Yeah, I think Javier was referring whether you see a difference when the alpha is rational or irrational.
Oh no, you don't. No, there is no difference there.
Okay, and we have another question by Luis Rax that says, thanks very much for the talk. Is there a three-dimensional analog of this system?
No, to be honest, I have no idea if there is a three-dimension. So I think that this kind of, for observing this kind of features, you need actually a two-dimensional system. And to be fair, yes, I don't think you can observe these features in 3D, but I'm not completely sure. So yes, one should sit down and try to do this calculation.
Okay, so with this, I thank Daniele and all the previous speakers because they have all kept very well the time and they have given very nice talks. And with this, I close the session and we reconvene in 15 minutes. Okay, see you later.
Of the workshop is going to be divided in two parts. One before the coffee break and the other one after the coffee break. There are two talks in each part. And the first speaker is Marco Lonchar from Harvard University. And the title of the talk is Quantum Photonics with Diamond and Lithium Niobate. So, Marco.
Perfect, thank you. Thanks so much for invitation and for giving me opportunity to visit Spain virtually. I guess hopefully soon we will have a chance to see each other again in person. So I wanted to maybe provide a brief update and kind of some of the exciting projects that have been going on in my lab for the last few years, since I guess I was at a conference in person. And so roughly split in two parts. First part, I'll tell a little bit about progress with Diamond, and then second part, which is somewhat new platform for us for both classical and quantum photonics, which is lithium niobate platform. But both of these are actually motivated by development of quantum interconnects, which is something I actually want to mention next. Before I go there, I just want to mention the team, current and past students and postdocs who can contribute to this talk in case I run out of time. So roughly the group is split in two, and half of the group does something with Diamond, which are the blue people here, people whose names are in blue. And it's mostly quantum work, with few exceptions of high power laser optics. And the rest of the group, another half, does work in lithium niobate, which tends up to now has been mainly on classical communication, but actually now, as you'll see, we are looking into application in quantum space and synergies with Photonics as well. And this is all motivated by this emerging kind of field of research that we refer to as quantum interconnects, in analogy with optical interconnects used for classical communication and computation. As these kind of quantum systems, quantum technologies mature, and we start connecting them in larger and larger networks, interconnect bottleneck kind of is becoming a little bit of the problem. And actually, last year, almost a year and a half now, NSF organized this workshop, and a bunch of people got together and were thinking about what are the challenges and opportunities in developing quantum interconnects, with a kind of particular focus on improving chip scales, quantum systems like a chip scale, let's say quantum processors, be it quantum computers, photonic quantum computers, or more simpler kind of quantum processor for quantum repeater applications, or try to understand what are the opportunities, what would be the role of photonics for, let's say, mid-scale or lab scale, if you will, building scale quantum networks, where you would be connecting, for example, quantum computers based on superconducting qubits, that in order to scale this platform up, you would essentially, the understandings at the moment at least, that you would have to go down the modular path, that you would not be able to fit all quantum computer in one devolution refrigerator. So you would need to connect multiple devolution refrigerators, for example, and photonics can play a major role there. And then finally, continental and also planetary scale, if you will, are these long distance quantum networks, quantum internet essentially, that allow you to, again, do distributed quantum computation, that coherent end-to-end, and so on and so forth. And I want a small advertisement, I guess, following great success, or synergistic with great success of quantum, or inspiration rather, of quantum flagship in Europe. Actually, NSF has recently started a center for kind of quantum internet, if you will, that's based in Arizona, University of Arizona, and myself and a few other people at Harvard and MIT are part of that as well. So, so here what we are working on are developing two main components. One is quantum repeater node, and the other one is quantum transducer. Quantum transducer would allow you to connect, for example, to superconducting qubits using optical fiber, and quantum repeater would allow you essentially to extend the reach of quantum network beyond what's limited by optical losses. And so for the first part, roughly first part of the talk talks about quantum memories in Diamond, that is essential component of quantum repeater, and progress on those front. And second part of the talk talks a little bit about lithium niobate platform and some first step towards realizing quantum transducers to convert microwave photon to telecom photon, as well as other possible applications of the lithium niobate quantum photonics platform. So, so first part, basically, as I mentioned, is focused on quantum repeater, and here we are really interested in quantum memories in Diamond. And so community is maybe mainly familiar with nitrogen vacancy color center in Diamond, as illustrated here. It's basically defect in the carbon lattice of Diamond, illustrated by blue balls, where you replace one carbon atom with nitrogen and then knock out another carbon atom and make this vacancy. And this color center, basically, when it becomes negatively charged, can be a wonderful wonderful memory. Electron speed can be used as a memory, and also you can reach out nearby nuclear string to make even longer lived memory. And then you can address this memory optically and using microwave. And wonderful work has been done, as I mentioned, by community. A lot of work has been done in Europe, of course. And one of what has emerged as a grand challenge for NV center in diamond is actually that while being very stable quantum emitter in a bulk diamond, it actually becomes very unstable when you put optical nanostructures around diamond, which you do need to enhance, for example, zero photon line emission shown here by this very narrow line. As kind of answer to this problem, there's new color centers that have emerged, and in particular, promising color centers are these so-called group 4 color centers in diamond, of which silicon vacancy color center is perhaps the best studied one, especially negatively charged silicon vacancy color center. Others are germanium vacancy, lead vacancy, and more recently, very promising one, which is tin vacancy. So these are group 4 elements. There's an interstitial defect, so they're sandwiched between 2 missing carbon atoms. And why these things are really interesting is because they actually have inverse symmetry, and therefore they don't have permanent dipole moment, and therefore are actually, to first order at least, not sensitive to charge fluctuations on the surface of diamond, which was one of the main issues of why NV center was so unstable in nanostructures. So these guys are much, much more robust and more stable in nanostructure, which is great. Unfortunately, due to very strong spin orbit coupling, these actually suffer from decoherence processes that are driven by phonons. So even at 4 Kelvin, actually, phonons drive orbital transitions that then impact negatively spin coherence. And solution to this, and this was done originally by Michel Lutin's group and also Matt Editor and Christian Becker, done some nice work when they were cooling silicon vacancies in dilution refrigerator down to 10 millikelvin, so where you essentially eliminate phonons, and then your spin coherence times becomes very, very long. So now, if you are willing to put money up and buy dilution refrigerator and do these experiments at very low temperature, actually silicon vacancy is very promising color center. But as I said, other opportunities are, especially tin vacancy color center, which could only potentially operate even higher temperature. So a few years ago, we switched from working with NV center exclusively to silicon vacancy center, and then kind of what my group had been working on, in particular, is development of the Diamond Photonics platform that would allow you to actually increase coupling between photons and these spin memories based on silicon vacancy center. And this is a work, long collaboration we have had with Michel Lutin's lab. So basically what we do, we make these diamond cavities by using processes, so-called angle etching process. I'm not going to go into details here, that were developed to carve high-performance devices in diamond. So this is photonic crystal cavity in diamond that's tethered to diamond substrate. This is actually very important for proper thermal syncing these devices, so that they are truly at millikelvin temperatures. And then we also have these tapers where we land actually tapered optical fibers. And nowadays, we can get a very nice coupling efficiency from the fiber to diamond and back to the cavity. And even in the dilution refrigerator, this can be like 90% or so. So what has been kind of a remarkable process over the last few years, and I don't know, that was the last time we actually met and been asked, but simply, maybe not so simply, but that the cooperativity of spin-photon interface that this cavity provides has improved tremendously over the last few years. And this was mainly driven by actually fabrication optimization, right? Just learning how to make these devices better and better. Optimizing fabrication processes with a little bit of improvement came from changing cavity design by reducing mode volume, basically. So by kind of optimizing placement of color centers using targeted implantation, through apertures, by optimizing fabrication process cooperativity, we were able to increase them from 1 to about 100, which enabled all kind of interesting experiments, some of which are listed here. And a particular highlight that I want to point out is this work was led by Misha's guys, collaboration with also with Dirk Engel and my group and Hong Kong Park's group of basically memory-enhanced quantum communication that for the first time shows that actually using memory, you can improve upon communication speed and or reach compared to memory-free communication, for example. So, and then there's many, not this session, we are looking to scaling this technology up now and really use it for quantum networking at large scales. And then there's a lot that needs to be done, and maybe touch on some of these challenges and also towards the end. One of the kind of tricky parts here that needed to be overcome is how do you tune quantum emitter to optical cavity? Because when you fabricate cavity, you never have perfect alignment. And so actually a few years ago with Mete Atatürk, we developed strain tuning technique, where basically what we do, we, in this case, we made some diamond cantilevers, and then basically by applying bias, there are some gold electrodes, by applying bias to these gold electrodes, we were able to deflect the diamond cantilevers, and therefore induce the strain at the color centers that are the clamp here. And due to, again, leveraging this spin orbit coupling, it's very, very strong. We now take advantage of them. Basically, you can change the orbital degrees of freedom, which allows you to change transitions, change the emission wavelength, basically, of silicon vacancy. But also it allows us actually to increase spin coherence time, which was kind of pretty neat, and we are still working on these ideas, by essentially splitting the ground state of silicon vacancy from about 50 gigahertz to even like 500 gigahertz. We were able to actually to increase spin coherence time even at 4 Kelvin temperature. So, so maybe there is hope to actually use silicon vacancy. And if not, then certainly thin vacancy at 4 Kelvin temperatures, so you don't have to go to these very, very low temperatures for quantum repeater application. But here we really mainly wanted to demonstrate that we can tune silicon vacancy with respect to the cavity. So this is experimental data that shows how by applying voltage, we can actually tune the emission wavelength of these 4 different transition lines. And then we went a step further and actually incorporated these tuning mechanisms with our photonic crystal platform. So this is kind of the latest kind of incarnation of this approach. So here is your diamond waveguide. Bright regions are gold electrodes. On this side, you have gold tuners. So you apply bias between top gold and bottom gold. This deflects diamond, and then it actually kind of affects controls essentially the emission of silicon vacancy color center. And with that, we were actually able to do a few things. First, we were able to address spectral diffusion. So even though silicon vacancy is more stable than NV, it can still spectrally diffuse. And this is actually not well understood. It's thought that maybe it's due to strain variation in silicon vacancy environment. So this is emission from silicon vacancy in one of these diamond nano waveguides. But what we can do, we can apply strain feedback. So we apply essentially by controlling the amount of voltage that we apply to these tuners, we can move diamond beam a little bit, which adds strain, and that therefore can overcome any spectral diffusion, and we can get very nice stable emission. So this was kind of demonstrated. This is essentially silicon vacancy emission with the lock on, with the feedback loop closed, and this is without feedback. Also, you can overcome homogeneous broadening, which was really one of the main challenges, in addition to aligning silicon vacancy with the cavity, we can also align 2 silicon vacancies. In NV case, maybe, or other kind of quantum emitter case, you would use this using Stark tuning. Unfortunately, because silicon vacancy is not sensitive to electric field, that's not an option. So what we use strain to overcome homogeneous broadening. And so here, for example, we show 2 silicon vacancy emitters in the same waveguide. One is further away from the clamp, so it doesn't really tune with applied strain. And the other one is actually far away, close to the clamp, so it tunes very nicely. And as you can see, as we apply voltage, actually we can bring one of these color centers in resonance with the first color center. And when we do that, we confirm basically you can get this kind of super radiant emission. You can get basically these 2 guys to be indistinguishable. So this is now being also adapted, and we are combining this strain tuning with the optical cavities. Maybe I'm just going to go real quick to this slide here. And we are trying to use it both to align silicon vacancy to cavity, and also to align multiple silicon vacancy to be emitting at the same wavelength. But maybe another kind of interesting opportunity here, which emerged from this work, because response of silicon vacancy to kind of mechanical deformation is so strong, we started considering alternative to building quantum network. So instead of coupling spins by using photons to mediate spin-spin interaction, we are exploring alternatives, which is based on using phonons. So ideally, we would like to use mechanical mode or acoustic mode, vibration more broadly to couple multiple spins. And so that has some interesting advantages. The most important one is perhaps that this kind of coupling always happens in ground state of color center. So we do not have to actually go through excited state, which would limit basically the spin coherence time to a lifetime of emitter. So if we actually operate in a ground state, the lifetime spin coherence time can be in the order of tens of milliseconds and milliclimate temperature. So gamma is very, very low. Mechanical quality factor, mechanical loss can be a problem because we operate the mechanical frequencies that are much smaller, typically gigahertz, 10 gigahertz, much smaller than hundreds of terahertz of optical frequencies. So even maybe and Qs are smaller. So basically, kappa can be pretty substantial, and also coupling can be reduced. But because we pick up this very nice spin coherence time, actually cooperativities, as I show on the next slide, can be very, very large for spin-phonon interaction, single phonon, single spin cooperativity. And basically, the goal is to use optomechanical crystals and operate everything 100 millikelvin temperatures. So we are also now doing these experiments in a delusion refrigerator. So the structure looks a little bit like this. It's pretty much the same as our photonic crystal cavity for spin-photon interface. This is now the one that's used for spin-phonon interface. Main difference is that this cavity actually now operates at 1.5 micron wavelength. So we can also nicely take telecom photon and indirectly interact with spin of silicon vacancy by leveraging mechanical motion, basically. And so these devices have optical modes, as shown here. This is modeling, have mechanical modes. There's a few different mechanical modes that we can leverage. We have fabricated these over the years. So this is optical transmission that shows optical resonance, and this is mechanical resonance. And so when you look at the strain of some of these mechanical modes, you can actually do detailed calculation. So this is cross-section of our structure. And you can see that depending on the mechanical mode we're looking, strain can be localized close to the surface or in the middle of diamond resonator. And then what you do, you essentially implant to silicon vacancy in the maximum strain intensity. And then we apply B field to use Zeeman splitting to split essentially the spin levels so that the splitting is the same as microwave frequency, which is, as I said, is roughly between 5 to 10 gigahertz, can be even higher. And then essentially what we have essentially spin interact with phonons, and we can get phonon-mediated interaction. And it turns out that, again, owing to very, very low, especially milliclimate temperature, very long spin coherence time, and very low kind of dephasing, spin dephasing rate, actually cooperativity of this phononic interface can be much, much better than cooperativity with a photonic interface. Plus, you're not suffering from photon loss rate, which is one of the problems for kind of wiring up spin system using light, for example. So we are actively pursuing this. There was recently very nice work from Paul Barkley's group where they demonstrated using the mechanical modes of disk resonators in diamond, demonstrated interaction between spin and mechanics. In our lab, we also, in addition to photonic crystal cavity, have been looking into even simpler structures, which are basically just use surface acoustic waves. In this case, we are not actually looking to couple two silicon vacancies in this way, but what we are looking is to do coherent control of silicon vacancy spin by simply launching surface acoustic wave. So basically, the system has aluminum nitride at the top of diamond, and we have these interdigitating transducers that we apply microwave field and they generate acoustic waves. And with this, we were able to demonstrate spin control. This is a Rabi sequence, and this is Ramsey experiment. And what's really nice, and we actually now have these, this is like just really fresh result from the lab last few weeks. using this approach, we were able to perform dynamical decoupling, and essentially for the first time in extended coherence time of silicon because it's been using acoustic waves. And what's really neat is that actually power budget, microwave energy is needed to actually do this is significantly smaller than what you would need if you were to drive spin using more conventional microwave driving, right, without acoustics. So we are really excited about this. And it could become an interesting tool for kind of controlled spins. Also, what we are looking into is how we can kind of scale this up. And this is actually kind of similar to some very nice work that Dirk Engel's group at MIT has demonstrated, where they combine diamond with aluminum nitride. In our case, we are interested in combining diamond kind of in general, some sort of photonics platform. And the question, and we would like this photonics platform to be able to allow us to, you know, have a nice coupling between diamonds, spins, and waveguides. We would like this platform to operate in visible and telecom wavelengths, so it can also do very efficient frequency conversion from telecom to visible, because we need to go to telecom range to propagate over long distance. We also would like to have very fast switches and modulators to control precisely spectral and temporal profile of photons emitted by silicon vacancy. And so the platform that we think can really enable all of these things is lithium niobate platform. This is a little bit busy slide, but lithium niobate, integrated lithium niobate photonics, which brings me to the second part of my talk. It's going to be a little shorter. Integrated lithium niobate photonics is actually a very nice opportunity to kind of do all of these functionalities on the same chip. And lithium niobate is well-known material for quantum photonics, and there's some examples of what people have been using. Kind of conventional lithium niobate devices, which are typically defined in bulk crystals, so they're like really large, not nanophotonics based. Perhaps the most well-known application is photon pair generation and quantum frequency conversion, which is something we're pursuing as well. But actually what we have been working on for the last 10 years or so is scaling this platform up in terms of complexity of photonic functionality we can have on a chip, and scaling it down in terms of how small of a waveguide we can make to increase interaction between light and matter, right? So these are some highlights, most notably using this kind of lithium niobate on insulator platform. So you have roughly half micron lithium niobate on top of silicon dioxide of silicon. And by optimizing fabrication processes, we were able to increase quality factors of lithium niobate devices orders of magnitude. That is reduce the loss down to 3 dB per meter, which is essential for any sort of photonics application. We demonstrated with Marty Fair also periodically cold thin film lithium niobate platform that allows you to actually do frequency conversion to go from, let's say, red photon to telecom photon. We have very nice, very fast modulators, the bandwidth in hundreds of gigahertz that can operate very low voltage, very important for photon shaping. And also we can realize various types of frequency comps that could be interesting for some sort of frequency domain quantum computing. I'm going to briefly mention. But kind of motivation for this application, first motivation for application of lithium niobate in quantum for us was actually try to see if we can make these quantum transducers where we would want to take one microwave photon emitted by superconducting qubit and turn it into one optical photon. So this is kind of, that was the idea, and the question is, can this be done? And so the platform that we started working on had been working on for some time now, and it's actually pursued now by a few other groups around the world as well. Amir Safavineni at Stanford and Hong Kong at Yale are also doing similar work. Are these photonic molecule platform where what you see here is 2 lithium niobate ring resonators coupled to lithium niobate waveguide with microwave electrodes around it. And basically, the way to understand this, why we call this photonic molecule, well, this is transmission of light through the ring resonator, single ring resonator. You have nice transmission dips. But if you couple 2 ring resonators, each of these dips actually splits in 2, so you have doublets. And splitting between these ring resonators is kind of controlled by the distance between the rings. So what we would like to do, we can tune this splitting to be the same as microwave frequency of microwave photon that is used for superconducting qubit, and then essentially do some frequency up conversion like this. We can think of this as essentially 2 coupled quantum wells. So a single ring is single quantum well, 2 rings are 2 coupled quantum wells, and then we use microwave photon to drive transition between 2 different modes, super modes in a quantum well, that are basically these 2 doublet modes, essentially. And so then what we want to do, so this is not drawn in frequency domain, we want to pump lower frequency of the doublet And then this is very similar to optomechanics. There were beautiful talks in this conference on quantum optomechanics. Pretty much the same Hamiltonians, except here instead of mechanics, we're using electric field. So this is Electro Optics actually, in fact. So we take, we have our optical mode here. We pick up one microwave photon and scatter one optical photon from this strong pump field to larger frequency. And you can optimize this so that the cooperativity are very, very large. Nice thing is that we can put many photons here to increase the process and increase the fidelity of this process. Limitations, how many photons we can put, are typically how many photons we scatter in the evolutionary refrigerator, and how many photons we can scatter before superconducting stops being superconducting. And I can unpack to discuss this in some detail. So this is the structure. It's very similar to the one I showed before. Here's lithium niobate waveguide. And this is work done actually in collaboration with Carl Bergen and Bill Oliver at MIT. So these are lithium niobate waveguides with superconducting microwave circuitry. There's no qubits yet. And so, these resonators can have very nice Q factors, about over 1 million. Microwave Qs are not as high, but it turns out they're decent for what we are trying to accomplish. And the main issue we discovered is actually the piezoelectric loss due to the lithium niobate strong piezoelectric response, which is kind of a little subtle. And so using this approach, currently we have conversion efficiency. I'm skipping a lot of details here, but we have roughly conversion efficiency of 10 to the -5, which sounds like really, really bad, very inefficient way. But it turns out that there are actually very simple improvements that could be made that are summarized in this table that essentially give you a 10 to the 5 improvements in this transduction efficiency for microwave optical photon, and which will bring you to this efficiency to be 1, basically. And in fact, recently, Hong Tan's group following this work and also very similar work from Amir Safavi and Amy's group in Stanford was published together with our work. Hong Tan's group recently demonstrated this efficiency in the order of 1%. And so, this was really done just for the optimizing, mainly actually minimizing how much light you scatter in the fridge and minimizing photorefractive effect of lithium niobate. What we are looking into is actually different strategies to do quantum transduction, in particular, those based on entanglement and teleportation. So basically the idea is to use, not to do direct conversion, microwave to optical and send optical photon over the distance to another fridge, but rather actually to do spontaneous parametric down conversion, where you generate one microwave and an optical photon, store microwave photon inside superconducting qubit and send optical photon over long distance, interfere them with Bell measurement, and essentially project entanglement back. Very similar to what, let's say, Ron Hansen's group has done with NV Center. Many other groups have done with different type of devices. There's a nice theory paper that summarizes this actually collaboration with Eric Englund and also with Rigatti, which I forgot to mention here. I think I still have maybe a minute or so. So maybe other thing that I want to say is this photonic molecule. So this was transduction. So we're working towards kind of conversion efficiency of 1 and increasing communication rate between microwave and optical. Very good progress. In the meantime, we actually figured out that the same device could be used for kind of frequency domain quantum computing. And I will not have a lot of time to talk about this in detail, but I will say that, for example, if I take this double ring resonator system and I drive it hard, don't use single microwave photons, but use very strong microwave drive, I actually start seeing like dress state. I see this resonance splitting, so oscillatoron splitting, whatnot. Or in time, you can actually observe Rabi oscillation. And so basically what happens, photon goes from one resonance, one of these doublets to another, and goes back and forth, kind of oscillates, right? So what we actually wanted to do for a while now is generate single-sided modulators, or if you want, you can think of them as frequency shifters. So this is the device where you put light in one of these resonances, apply microwave, and you end up in this resonance. So it's same as microwave to optical converter, but works with a lot of light and a lot of microwave. The problem with this kind of concept, as originally envisioned, is that you need to actually stop microwave. You need to kind of interrupt microwave pulse when you convert light from one resonance to another, which is inconvenient. Anyways, with some optimization, we were able actually to overcome this. And I won't have time to tell you how, but this is experimental data that shows that now our device can do essentially 100% conversion efficiency with very low insertion loss. So basically what happens, you put light at, let's say, 737 nanometers, apply RF field, continue sine wave RF, and we shift this light with 12 gigahertz with 99% efficiency. And so this is really nice. We are now using this actually to kind of fix the emission wavelength of silicon vacancy color center. That's one envisioned goal. If a color center emits a different frequency, we can send it through this device and shift its emission frequency a little bit, and then we can overcome homogeneous burdening like that as well. Another nice application of this is, and I'm just going to stop here, is in frequency domain quantum computing. And skip a few slides, but it turns out if you dial down microwave power, actually, this frequency shifter becomes frequency beam splitter. Instead of, it's equivalent, a frequency equivalent to spatial directional coupler or wave plate polarization encoding of the qubit. So using this device, we are really thinking we can maybe implement these ideas put forward by Joe Lukens and Pavel Ludowski on using actually frequency domain of photon to do photonic quantum computation, linear optical quantum computing, where basically we rely on some electro optic effects and wave shaping. We think we can actually address this with our device. And so maybe I just leave you with the last slide here, which is some other opportunities we are pursuing with lithium niobate, including the fact that actually we have a small startup that's commercializing this technology, and this is actually some 6-inch wafer lithium niobate with a lot of classical and quantum devices on it. So if this is something of interest to you, I'd be happy to collaborate. Thank you so much for your attention, and sorry I took a little longer.
Okay, thank you, Mark, for the very impressive talk. So we have time for 2 questions. That is a question and comment by Klaus Roppers. A great talk, thank you. I was wondering if there was a possibility to fabricate the silicon vacancy aluminum nitride structures with a total thickness compatible with electron microscopy, down to 200 nanometer or less.
So basically this structure, so I actually forgot how thick is aluminum. You mean the whole stack, aluminum nitride and diamond to be 200 nanometers. So it's transmission, I'm assuming that's the case. Yeah. So this is done on bulk diamond for convenience. We are actually looking into doing this on thin film diamond as well, because that will increase effect. I mean, if there's some amazing physics, Klaus, that you have in mind, I'm going to go with yes, and let's discuss it. It'll be painful, but could be tried.
Okay. Okay, so there is another question by Daniel Riedel, very nice talk. Using your strain tuning technique, do you distort the symmetry of the silicon vacancy center? Can you use strain tuning to tune the optical resonance of the cavity?
Yeah, so it's an interesting question. So I guess if you distort the symmetry, I mean, we definitely change orbital a bit. So we were worried if we destroy the symmetry too much, especially if we sometimes were able to go to terahertz splitting from 50 gigahertz, it's tons of strain, that actually we would maybe start being sensitive to kind of electric field fluctuation, but we haven't observed that, to be honest. So I'm going to go with no. We could strain tune, we could actually do mechanical deformation of the cavity. We have also pursued, well, we have been thinking about pursuing this as well. This is very nicely can be done with this isotropic undercut method that I know that Daniel, you're working on, and Niana's group. Answer is yes. We have slight preference to actually tuning emitter, and we plan to tune then address all other misalignments using linear optics, basically. So that's, but that's what we are thinking. There are other ways to do this, including what Daniel suggests.
Related to that, I mean, apparently the spin coherence increases when you have a strain.
Yes. Yes.
The physical picture of
why?
Why that is?
Yes. Thank you for that question. I completely glossed over it because I tried to cram 2 different subjects in one talk. So at 50, so this is without strain. We have like 47 to 50 gigahertz splitting, and at 4 Kelvin temperature, which is where this experiment was done, you still have like 10 to 15 phonons that drive these transitions, and you ruin your spin coherence. When you strain it, you split this to a hero device, even 1 terahertz, more traditionally maybe 400 or 500 gigahertz. So now at 4 Kelvin, you don't have 400 or 500 gigahertz phonons. Okay. So there's no essentially decoherence phonons.
Okay. Thank you. There is another question that perhaps you can use the chat to answer Martin Somajewski, because it's...
Yes, I read it. Yes.
Okay.
Yes, that's kind of, we are looking into this, to that couple directly to lithium niobate. Yep, that was the goal.
Okay, thank you, Marco, for the nice talk. And we have to move on to the next speaker that I hope that is prepared. Is ready for the, is Moritz Fischer.
Yes, 1 second.
Okay, so he's from DTU, Denmark, and the title of his talk is A Generation of Luminescent Filters in Hexagonal Boron Nitride by Irradiation Engineering. So Moritz,
Yes.
all yours.
Thanks for the kind introduction and welcome to my talk. My name is Moritz Fischer from the Technical University of Denmark. And today I'm going to talk about the generation of luminescent centers in hexagonal boron nitride by irradiation engineering. And hexagonal boron nitride is a member of the family of two-dimensional materials. So after the discovery of graphene in 2004, several two-dimensional materials have been discovered, including hexagonal boron nitride or HBN. And the characteristic of this material is that they have strong in-plane bonds and weak out-of-plane bonds. And that makes the advantage that you can stack them. So to make this called heterostructures that you can sketch down here, see down here, without matching a lattice constant. So you can think about many different stackings and devices for applications. And the material we are interested in is hexagonal boron nitride. You see a monolayer sheet here. It consists of hexagons with alternating boron and hydrogen atoms. That material is an insulator with an experimental band gap of around 6 electron volts, and it can host luminescent centers, like you see here. So this is a photoluminescence as a function of wavelength. And the advantages of these luminescent centers are that in the monolayer case, you don't have any surrounding crystals, which gives you high coupling efficiencies. And also coupling possibilities in that sense that the emitter is very close to the surface. So for instance, if you want to couple it to a plasmonic nanoparticle, you can put those two very close to each other. And then, as I said, it's a member of this two-dimensional material, so you can play 2D Lego with it. You can stack it on top of each other and think about many different devices for later applications. And the luminescent centers in HBN, they attracted a lot of attention because they showed room temperature quantum emission. So this is indicated here by this G2 or second order correlation function. And if you get a dip at 0 time delay below 0.5, then you have a non-zero single photon contribution. And on top of that, it's also ultra bright. So it also showed to have emissions of millions of counts per second. And so these quantum emitters have been discovered around 5 years ago. So it's a relatively young field. So there are some challenges. And I would say most importantly, the microscopic origin is still under debate. And also we're having quite a large spread of optical properties reported. So the zero Foner line is a few hundreds of millielectrons different from luminescent center to luminescent center. And also the generation is mostly uncontrolled. So during my PhD project, we set ourselves the goal that we want to controllably generate those luminescent centers. And what do we mean by this? By this, we mean that we only create one specific type of defect. And on top of this, we would also like to understand the generation mechanism, so how this one type of defect is formed. And by this, of course, we can provide insights into the microscopic origin, which is one of the main challenges of the field. And before I start with our generation process, I want to give you a few processes tried in the literature. So first and most common, I would say, is annealing of low quality HBN, which led to this large spread of optical properties here. Then people also tried electron irradiation, and then they got the spectra like shown here. And this electron irradiation was also carried out on high quality HBN, so they also got luminescent centers. And then this high quality HBN was also used to make a bit more complicated process, which is oxygen plasma followed by annealing. And then they found also luminescent centers with a similar line shape as with SEM. And here, remarkably, they found a depth selective generation. So they figured out that the luminescent center is located in the 4th layer from top in most of the cases. And for the experts on the field, just what I mean here, so low quality HBN is obtained from graphene supermarket, and the high quality HBN is obtained from HQ graphene. And the processes I show here are really uncontrolled. So there are different kind of defects generated. And to address this control generation, we came up with a novel process, which is which starts with the exfoliation. So for those of you who are not working with two-dimensional materials every day, so you basically buy a bulk crystal, or you take a bulk crystal, and then you really take a Scotch tape and you peel off and put it on your substrate as sketched here. And we use the high quality HBN, which only holds a few defects. I will talk about this later on in detail. And then the second step is the oxygen irradiation. So we irradiate with oxygen atoms, highly directional and with a narrow kinetic energy distribution. And then the third and final step is annealing at 850 degrees in nitrogen. And these steps we can basically trace an evolution by taking photoluminescence maps after each step. For instance, here shown for one HBN flake. And then by looking at the locations, we can trace the evolution of individual luminescent centers. So for instance, shown in this plot here, so this is the blue spectrum is after exfoliation, and the red spectrum after irradiation, and there you basically see no photoluminescence, while after subsequent annealing, you get a nice spectrum. And then we did this on another HBN flake and got this spectrum here in purple. And in general, we found two groups of luminescent centers, namely the group 1 showing a relatively sharp zero phonon line associated with phonon sidebands, and also group 2, which shows a broader zero phonon line with less pronounced sidebands. And then we also looked at them, okay, are our luminescent centers actually quantum emitters? And we used this group 1 luminescent center. We selected the zero phonon line here, and we carried out a G2 measurement. And we indeed get a G2 value well below 0.5, so it is a clear indication of a quantum emitter. And one challenge I would like to mention here is that the measurement times of these correlations are a bit limited because the luminescent centers, they tend to bleach after a certain time. And as I said, our goal is to controllably generate luminescence or quantum emitters in HBN. And for this, we studied more than 50 HBN flakes. And for now, we consider group 1 and group 2 together. And we quantified the amount of centers generated by taking the number of centers generated divided by the area. And this is what you see here. So this is the density after exfoliation, after irradiation, and after subsequent annealing. And you basically see only, so this is shown for 2 batches here. So for after exfoliation, you only get a few luminescent centers. This is reflecting the high quality of HBN we use. And then after irradiation, for instance, here for the batch 2, the centers basically disappear. And then after subsequent annealing, the density increases substantially. And that shows you a bit the control generation because there are only few present before our generation process, but then actually a lot after the final step of our generation process. And to study the generation process, we can basically tune the oxygen irradiation. And what we first did is we can tune the energy. And as I told you, we have a very narrow kinetic energy position, which is plus minus 5 electron volts. And we can tune the energy from 120 to 300 electron volts. And here you see the density for 2 different batches of HBN as a function of irradiation energy. And you see, so in solid lines, it is one batch, where you see that we obtain a maximum density at 240 electron volts, while for the group for the batch 2, shown in dashed lines, you can also see a linear increase with intermeasurement uncertainties. And to investigate this, we asked our colleagues in Dresden, the Helmholtz Centrum, to carry out some molecular dynamic simulations of the irradiation process. So this is the top view of the HBN, and this is the side view. So they use 6 layers of HBN, and then they shoot an oxygen atom with a certain velocity onto the target system, and then they can, in detail, predict what is happening with the atoms. And to quantify this, they provided us, or they can provide the number of vacancies generated per incident oxygen atom. And here I will use the following notation. So Vn is a vacancy, is a nitrogen vacancy, and Vb is a boron vacancy. And what you see, what molecular dynamics predicts is a linear increase with a radiation energy. While if we compare this to our experimental results, well, even if you take the batch 2, the linear increase is not as strong as predicted by molecular dynamics simulations, and we also provide possible reasons for this. One is during thermal annealing in nitrogen, the nitrogen vacancies are easily annihilated simply by splitting off a nitrogen molecule on the surface of the HPN. And then we also have a small positive oxygen contribution in our plasma, which cannot be simulated by molecular dynamics simulations. But if we look overall, we see that the influence of the irradiation energy on the generation mechanism is minor. And then we thought, okay, what else can we tune? Well, we can also tune the fluence. So the irradiation fluence, that's a quantity which is defined as the number of oxygen atoms arriving per area. And we basically tune this by changing the irradiation time, but keeping the flux constant. And these are our experimental results. So again, the density, and now in this case, is irradiation time. And here we really see a fivefold and substantially enhancement of the density when we increase the fluence. And we find this enhancement is stronger for group 1 than for group 2. And then we ask our colleagues in Dresden again, okay, can you also do molecular dynamic simulation of high fluences? And indeed they can, and in this case, they do it with multiple impacts. So you will see multiple oxygen atoms arriving from the top, and then the system is allowed to relax a bit before the next atom arrives. And you see that many oxygen atoms take in the target system, and more atoms are getting distorted here. And after our certain fluence with the number of oxygen atoms per area is reached, there is an annealing step performed at 100 degrees to on a nanosecond timescale to get rid of the metastable states. And the result is basically the following. So when you look at the first layer on top and side view, you see that there are a lot of atoms missing and a lot of distortions also out of plane. And the same goes for the second layer. So basically, the irradiation is amorphizing the top HBN layers. And this can be quantified by the so-called radial distribution function. And just to introduce you quickly to this, so the radial distribution function gives you the atom distance. So for a monocrystalline material, this is just delta peaks because the atom-to-atom distance is always the same. However, after irradiation, for instance, when we focus on the boron-boron distance here, we get a peak with a finite width telling you that there's a certain amorphization, was a certain amorphization going on. And this amorphization is increasing when from top to bottom here when we increase the fluence. And that means that as higher the fluence, as more amorphous our topmost HBN layers are. And that is, again, so this quantification, this is in good agreement with our experiments, because we also obtain a higher density of luminescent centers when we increase the fluence. And that tells you that this is the major influence we find on the density of luminescent centers. So that has to dominate the generation mechanism of these. So let's come to this. So as I told you, experimentally, the fluence dominates the generation mechanism. And describing the generation mechanism, so the irradiation is amorphizing the topmost layers of the HBN. And this is actually confirmed experimentally because for the batch 2, the luminescent centers present after exfoliation actually disappear after irradiation. And then during subsequent annealing, we say that the crystals, the HBN is recrystallizing, and just in such that a few defects remain, which are then responsible for our luminescent centers. And this is also confirmed by another experimental fact that the group 1 luminescent centers show sidebands, and these sidebands are addressed to bulk phonons of HBN, telling you that in the vicinity of the defects there has to be some HBN bulk material. So this is confirming the recrystallization. And now, having clarified the generation mechanism, we can even go further and study possible microscopic origins. So the irradiation generates, as I showed you, boron vacancies and nitrogen vacancies. But it can also form oxygen vacancies. So this is oxygen on the nitrogen side, and the double vacancy VBN. Then during annealing and also from impurities from the HBN itself, you can easily incorporate carbon into the HBN, leading to the CB and CN, so carbon both on boron and nitrogen sides. And also the annealing will provide nitrogen atoms on the HBN by just splitting the nitrogen molecule. And this will annihilate the Vn and the On, and it will transform the Bn to the Vb. And also during annealing, you can imagine that defects become mobile, so they can merge. For instance, the Vb can merge with the Cn to the so-called VNCb. And then, having found these 4 defects, we checked the literature. What does DFT calculation predict for the emission? And actually, the DFT calculation predicted the CB and the Cn, they don't have any emission in the visible. And that actually leaves us only with 2 defects that are most likely formed. So this boron vacancy and this carbon-based VNCb defect. And here are some sketches of these in the hexagonal boron nitride lattice. So here you see the VNCb, so there's a nitrogen vacancy, and here in black the carbon atom on the boron side, and here's the boron vacancy. And there was a recent work identifying that the single photon emitters in HPN are carbon containing, so this is in agreement with the VNCb, and also works with spin experiment assigned the responsible defect to VB minus. So that's why we picked these 2 defects for ab initio calculations of the photomedicine's line shapes, carried out by our colleague at DTU Physics. And this is what they get theoretically. So for the VNCb, they get a 0 phonon line associated with phonon side bands, while for the VB minus, they get a rather broad photoluminescence spectrum. And also just, so I want to mention, so these are ab initio calculations, so they don't have any fit parameters except a phenomenological broadening to mimic the temperature. And we now can do qualitative comparison to experimental line shapes, and we find excellent agreement of the group 1 with the VNCb defect and of the group 2 with the VB minus. And I want to highlight here that this is no identification of defects. We found excellent qualitative agreement, and we infer that these defects are responsible. Okay, so let me sum up what I've shown you. So I've shown you that our novel irradiation-based process can generate single photon emitters in high quality HPN. It is a way towards the controlled generation because those defects were not present before our process. I showed you the generation mechanism. So this is the amorphization during irradiation, then the recrystallization during annealing, just such that a few defects remain. We also inferred that the VNCb and the VB minus are responsible for the luminescent centers, confirmed by this excellent qualitative agreement with ab initio calculations. And the challenges are, as I mentioned, bleaching. So some of these luminescent centers tend to bleach. And also we would like to achieve site selectivity, because for column applications that is important. And our next step, which is already in progress, is to study the phonon coupling by low temperature measurements, in particular of group 1, to study these phonon side bands in more detail. And as a quick outlook, so we made a step forward towards the control generation, and we inferred these 2 defects to be responsible. What is also important to note is that our process relies only on inexpensive equipment. So we're using a refractive ion edge reactor and an annealing furnace. So in principle, you can easily apply this to other gap 2-dimensional materials to create luminescent centers in a controlled fashion, or even single photon emitters. And during the progress of my PhD, of course, the literature moved on. For instance, the chemical vapor deposition ground HPN showed a narrow optical response. So the 0 phonon line is not over hundreds of milli-electron volts in their case, as shown in the beginning of my talk. And also, there was this recent discovery from the group of Igor Harunovic, where they identified that single photon emitters are carbon containing. And as an outlook and goals, so of course, we would like to identify the microscopic configuration, so the exact one, and also achieve a controlled and site selective generation, because that is essential. We've seen so many nice quantum applications, and they require this generation. With this, I'm at the end of my talk. I would like to thank the organizers for giving me the opportunity to present my work. I would like to thank my 3 supervisors of my PhD, in particular Nikolai Stenger, who was my principal supervisor. I would like to thank the team in Dresden who did the molecular dynamic simulations, and also these 5 people within our nice center of nanostructured graphene who actually triggered a lot of that work I presented. Thank you for your attention.
Okay, thank you, Moritz, for the nice presentation. So now the panel is open for questions or comments. Okay, I'm going to break the ice with my question. I mean, do you foresee that with this method you are going to be able to control? I mean, just to create arrays of luminescent centers with this idea? I mean, you say that the challenge is to site selectivity. Do you foresee that at the end you are going to be able with this method to create, okay, a kind of control vacancies that you can create arrays or whatever?
Yeah. We have seen on Wednesday, for instance, that Igor presented that he uses pillars and puts the HBN on top. So one could dream about using strain to localize the emitters. And otherwise, I'm not an expert. I mean, of course, in principle, you could, like you can do with a helium ion microscope, where you can only shoot on a specific small area. I don't know if such facilities are available for oxygen, for instance. And then you could also, by this, make it a bit more local. Yeah.
Okay, any more questions from the audience? Okay, so if not, everything is ready everybody is ready for the coffee break apparently. So we have 10 minutes for a coffee break, or just to have a walk before we resume the session at 6:25. Okay. So thank you, Moritz, for the nice talk.
Thank you. It was a pleasure.
See you all. It's a pleasure to introduce Mohammad Bereihi from EPFL Switzerland, and the title of his talk is a high cooperativity silicon nitride optomechanical transducer. So Mohammad, everything is yours.
Thanks, Francesco, for the introduction. Hi, everyone. Thanks for being here. I'm Mohammed, and I'm from the lab of Professor Tobias Kippenberg at Lausanne, EPFL, and today I'll be talking about our recent work in room temperature cavity optomechanics. So just very briefly, why mechanics? Simply because they're very, very high quality factor harmonic oscillators. They're everywhere in our cell phones, accelerometers, and used also for timing. And for more fundamental research applications, they have been coupled to several systems, spins, ultra low masses, and also not to forget the gravitational wave observatory, which one of the key fundamentals are the LIGO mirror suspensions, for example. Mechanical oscillators are very interesting to study. However, if you want to enter the quantum regime, so-called, there are a few challenges. Mainly, here I'm talking about, for example, oscillators in the megahertz range. At room temperature, they have very high environmental occupation. Therefore, need to reach to their quantum ground state. You need to cool them down significantly, either putting them in a fridge or use cooling techniques. And in order to do so, you need very sensitive readout in the order of the 0-point fluctuation. And also, if you're using them for sensing, you need to be able to couple them to your system quite efficiently, which can be quite difficult and not straightforward. Radiation pressure, however, has shown for many years one of the building blocks of the quantum optics with the quantum control over levitated particles and also atoms and ions, which gave kind of the idea of using radiation pressure to control quantum systems, and cavity optomechanics started by exploring the same idea on a macroscopic mechanical system and gaining control over it via radiation pressure. Just very briefly, optomechanical system, you can think about it as a fiber cavity with the end mirror, which oscillates, and the motion of the end mirror is imprinted on the phase of the light exiting the cavity. And today I would like to emphasize on the dissipation rates of a real optomechanical system. In reality, the cavity can be lossy, and there are dissipations of the cavity. Also, of the mechanics, the dissipation of the mechanics can lead to thermal decoherence. And putting all of them together in one figure of merit is a single photon cooperativity of the system, which is comparison of the coupling over dissipation rates, and the cavity enhanced cooperativity of the system compared to the thermal occupation of the environment of the mechanical oscillator kind of shows the quantumness of our transducer. And whenever I talk about being in a quantum regime, I mean that the CQ parameter exceeds 1, which at that point the radiation pressure force starts to overwhelm the thermal force acting on the oscillator. Of course, one way to increase the quantumness of the system is to cool it down cryogenically, which has been tried in the field and has been very successful. However, if you don't want to do that and you want to stay in the at room temperature, just to give you an overview of that how difficult it might be, the thermal occupation of a 1 megahertz oscillator at room temperature is about 5 million. Therefore, you need a system which is has extremely high cooperativity, meaning that the dissipation rates of mechanics and optics are very low. And also, you need to keep these dissipation rates low whilst making achieving a very high coupling between the two, which can be challenging. Therefore, we have, let's say, we have a checklist to do. We know what we should look for if you want to do room temperature optomechanics in the quantum regime. And to start with, I will start with making low dissipation mechanical oscillators. To do so, we make use of the concept of dissipation dilution, which dates back to a design of the mass suspension of gravitational wave observatories and has been explored in the field of optical trapping and successfully recently in nanomechanics in the last 10 years. And the only thing you need to remember throughout my talk, whenever I talk about dissipation dilution, is that by adding stress to your mechanical system, you start diluting the dissipation, adding to the quality factor of your system. And you kind of can think it as an analogy of adding a lossless potential to your lossy harmonic oscillator. This rings a bell for which material to use. Obviously, we will choose a material that has already a high intrinsic stress that comes with the deposition of the thin film, and we don't need to therefore add the stress externally to the system, which in our case is LPCVD silicon nitride, which is already tensioned with about 1 gigapascal, give or take 5%, usually for this method. Looking at how much quality factor enhancement do we get compared to the intrinsic Q of the silicon nitride, which is, let's say, the dissipation dilution that comes from the stress. We can formulate it in this form, which has been formulated with this as a parameter of this lambda parameter, which is nothing but thickness over length, therefore the aspect ratio, times this factor, which is which comes from the material itself, Young modulus over the stress of the thin film. And for a high stress film, it's much, much smaller than 1. And therefore, you immediately grasp that this lambda parameter is what rules the dissipation dilution at first, which comes from the curvature of the mode at the boundaries. And by that, I mean, because the mode, as it reaches the clamping point, both the displacement and its derivative has to go to 0. And this leads to this lambda term, and this term proportional to lambda, therefore, first sources of loss. And the second term in red is corresponding to the distributed curvature of the mode itself, which increases as you go higher in mode number. To start with, we can try minimizing the alpha parameter, therefore increasing the quality factor to for the first step. And if you remember, as the notion of the dissipation dilution that I told you, a rule of thumb is to add stress where the losses are coming from. And in this case, they're coming from the clamping points. Therefore, by adding stress to the clamping point, which is simply by tapering the suspended structure, at the clamping points, we increase the stress, therefore increase the quality factor, and we can, on the other hand, expand and anti-taper the clamps, like in this case, and deteriorate the quality factor quite systematically. Minimizing this parameter even further, meaning that setting the alpha parameter to 0, which comes from the fact that you should engineer a mode that by reaching to the clamps, it should have 0 amplitude at the clamping points, which is the so-called technique of soft clamping that is achieved by having a mode localized in the center of the resonator, which is localized by introducing phononic shields. Excuse me. Moving one step ahead would be minimizing the losses that are ruling the system for a soft clamp mode, which are the distributed curvature losses. And this brings us to the point of strain engineering, which is again simply understood as the notion of dissipation dilution, which by increasing the stress in the center of the resonator where the mode is confined and where the losses are coming from, we can dilute dissipation, therefore enhance the quality factor. And in this design, we have a doubly clamped nanobeam, which has this corrugation, which generates phononic band gap, and the part in the center is tapered, similar to the clamp tapering technique, but in the region where the mode is confined, not at the clamping points. This technique works for higher order modes, as you can see very well from this mode shape. However, in case of a fundamental mode, there are other ways here, which we have developed recently, theoretically in the lab last year and recently experimentally demonstrated, are the fractal-like resonators, which have this branching at the resonator, and this hierarchy of the structure leads to reduction of the mode amplitude as it reaches the clamping points, for example, here. And here I have shown the mode profile of a fractal resonator, and you can see compared to a uniform beam, it has a 0 curvature at the clamping point. Therefore, the quality factor are much higher for a fundamental mode of the fractal resonator. Therefore, you can think of them as a soft clamped fundamental mode. Just flashing the results of what opportunities do we have working with high-stress silicon nitride for low dissipation mechanics. Depending on the application, we can choose clamp tapering, strain engineering, or fractal-like or hierarchical structures, depending on the frequency of the mode or how much enhancement we want or how much device footprint, for example, we can afford. Therefore, we have a lot to choose for. The first item on our list, which was the low mechanical dissipation. The next step would be thinking about coupling these oscillators efficiently to our optical cavities. And one approach that has shown to be very successful is the near field coupling, which is simply bringing close a nanobeam or the mechanical oscillator close to the evanescent field of an optical cavity, which has been explored in this field in the last 10 years, mostly in the approach of having the whispering gallery modes, in this case toroid or these two microdiscs, coupled to a silicon nitride nanobeam, integrated and discrete systems. And the good thing about near field coupling in this case is that you can optimize both systems individually, both optics and mechanics. However, using whispering galleries rings a bell for some improvement here. There's quite a bit of room for improvement. For whispering gallery mode, the overall mode extension of the optical mode is much larger than the effective interaction length. However, by unfolding this structure into a 1D structure, you can think of enhancement in optomechanical coupling. Therefore, by matching the dimensionality of optics and mechanics and having a 1D cavity next to a nanobeam, we immediately enhance the sampling volume of the optical mode. So everything on our list is ready to go. We know what type of cavity we're looking for: a 1D Fabry Pro cavity, a near field coupling to the high aspect ratio silicon nitride resonators. of different designs. And the overall system should look like this. Here I have chosen soft clamp nanobeams with a localized mode next to a 1D cavity, which we couple to via optical tapered fiber or tip etched fibers. And just to check, for the near field coupling here, I'm showing the simulation. And you can immediately see that the cross section FEM of the optical mode, you can see that the optical mode is strongly pulled by the nanobeam, and by choosing the correct thickness, we can actually be in a regime where the G naught of our system, the optomechanical coupling rate, exceeds 1 megahertz. And if you remember from the talk of Marco Lonkar, these values for G naught are in the order of optomechanical crystals, which in this case the advantage would be working with megahertz high Q mechanical modes, which would be very, very interesting regime to explore, of having such high coupling for such high Q resonators. Looking at the last element of the puzzle of the transducer, which is the 1D fabric pro cavity, our design is fairly simple. It's a single mode waveguide terminated by 2 photonic crystal mirrors at 1550. We use mode matching of adiabatic mode matching to match the mode of the waveguide to the mirror to open a band gap, photonic band gap at around 1550. In case you're interested in knowing more about this, the details and technical details of these simulations, I put a link and a QR code of a workshop we organized at EPFL a few years ago, where I talk about photonic band gaps. In case you're interested, you can have a look. And these cavities, despite being very thin, our designs are 250 nanometer thin silicon nitride cavities, and the modes the mode is very evanescent. The effective refractive index of the waveguide is about 1.2. We can achieve finesses above 100 quite reproducibly in our fabrication, and the highest finesse that we have achieved is about 200, which corresponds to 1.1 gigahertz total line width of the cavity. Having such high Q cavities, we also need to be able to couple the light in and out efficiently, which is very important for different experiments. We have integrated a waveguide, an integrated waveguide, which we can vary by fabrication the gap, and therefore we can sweep the coupling to the cavity from being extremely overcoupled to very undercoupled, and therefore it can be tuned depending on the need for the experiment, the coupling efficiency to the cavity. I'll be very, very short on the fab. We use a single stack of silicon nitride, and we have developed a thinning down technique to be able to tune how thick we want the silicon nitride of the nanobeam to be by opening a channel. And we finally released the structure using wet release and critical point dryer. And this is the final an SCM of a final release device of a nanobeam. Here you can see this is a clamp taper design next to the cavity, and this is the integrated waveguide to couple the light in by the tapered fiber. And here I'm putting a link to an open science initiative that we started a few months ago at EPFL called Nano-FabNet, which is an archive, which we're aiming to be, let's say, an archive for fabrication reports. And here we were aiming to collect different fabrication run cards and different details of failures and successes in fab, things that might get neglected when writing a publication or skipped while giving a talk due to the lack of time, for example. So yeah, in case you're interested in a research group, have a look. And the last part would be to characterize the optomechanical transducer. And here I'm showing the Brownian motion of the nanobeam, optical and optomechanical characterization by spring shift, and the mechanical quality factors are determined by doing mechanical ring down by the cavity. And overall, we have achieved so far the optomechanical cooperativity, the C0 for the in-plane mode of exceeding 1000, which corresponds to a 660 kilohertz G0, an overcoupled 15 gigahertz cavity, and mechanical line width of 300 millihertz, which is which allows us to explore a lot in such a system and try to look at different possibilities for different experiments. Since such high C0 values are among one of the highest for an integrated system, comprising a megahertz oscillator in our case, a nanobeam. With that, I come to the end of the talk. As a summary, I put the building blocks of what we need for a high performance room temperature optomechanical transducer to be able to enter the quantum regime and be able to exceed the quantum cooperativity of 1 at room temperature. In order to do that, I showed you the designs of different mechanical oscillators, and depending on the need, which type to explore for our transducer, and also the result of the transducer, which we could achieve C0 exceeding 1000. And such a system will allow us to observe quite interesting effects, hopefully in our transducer. To name a few, observation of QBA on the oscillator, also generation of non-classical light, and also feedback cooling of such a high Q oscillator to the quantum ground state, hopefully. And with that, I would come to the end of the talk. I would like to thank you for your attention, thank the team at EPFL, and also the funding agencies that make all this possible. Thanks.
Thank you, Mohammed, for the very nice talk and presentation. Just on time, perfect. So, okay, the panel is open for questions or comments. Okay, so I have to break the ice again. So, I mean, yesterday we saw the talk of Paul Seidler, and today the Marco Launcher. So they were trying to do a kind of transducer also, but they were using, I mean, the mechanical, let's say the mechanical mode and the optical mode were made on the same system. But in your case, you have two different structures. So yes. What is the advantage or disadvantage of this with respect to the others?
So that's actually a very good point. The advantage here for us is that we're working with the flexural mode of a nanobeam, which is engineered and designed separately of the cavity. Mm-hmm. However, and such a design allows us to have quality factors of in the order of hundreds of millions, for example, at megahertz frequencies, compared to, for example, the modes of, for example, the optomechanical crystals of the optical cavity itself. And the advantage of our system is the high quality factor, mm-hmm. given the fact that the G0 that we can achieve for such a design is actually quite comparable to the works of optomechanical crystals, because we have so far gotten to 660 kilohertz, which is on par with what people get in for example, silicon, diamond, or gallium phosphide optomechanical crystals. But here we have a high Q mechanical mode.
Okay, thank you. So we have two questions. One from Mats Christensen. Thank you for your talk. Have you studied absorption heating in these cavities?
Actually, yes. We haven't studied in details. We are starting to explore because we have got the final devices with high performance just a few, let's say, months ago. But we have seen effective heating and absorption depending on the wavelength of the resonator. And also, since we work in vacuum, we have seen that heating at some point starts to break the Lorentzian of the cavity, and the resonance starts to become thermal, which can be also a challenge for future experiments.
Okay, we have an additional question from Yunxing Chen. Interesting approach. Are the optical resonator and okay, I think that you have answered this question. And mechanical resonator on the same chip? So
yes. It's an integrated platform. Both of them are sitting on the same chip.
And the other question, I think that you answered. What is the material for the optical resonator?
Silicon nitride.
Silicon nitride. Okay.
I think it's the title of the talk. Yeah.
Yes. Okay, so if there are no more questions, I think that we can move on. Thank you, Mohammed, for the nice presentation.
Thanks for having me.
So the next speaker is Javier Del Pino. I think that is prepared. So he's from Amorf, Amsterdam, and the title of his talk is Synthetic Magnetic Fields for Topologically Protected Sound in Nano-Optical Array. So it's related to nano-optics in this. Okay. Javier, it's all yours.
Yeah, thank you very much. And thanks first to the organizers for giving me the opportunity to present my results today, and which have been developed during my postdoc at Amolf, where I work as a theorist. And this work has been done under the supervision of Ebol Verhagen. And most of the results that I will present today are experiments performed by a PhD student, Jesse, and a former postdoc of the group who is now working on industry, John. So in this talk, I will describe our efforts to manipulate nanomechanical vibrations. And the motivation to do so has been already introduced by many of the previous speakers. I just highlight here two of the interesting avenues. So first, nanomechanical systems can be used to build, using very high quality factors, resonators, nanomechanical sensors, which are very sensitive and have frequency shifts that are measurable even when they are absorbed single molecules, and this can be used to build sensors with down to the joctogram resolution. But also there are efforts on using many of these nanomechanical systems interfaced and exploit their intrinsic nonlinearities to simulate other systems that are otherwise very hard to simulate, like Ising spins. And here I take the chance to stress that what I will mean with sound is the mechanical energy propagating from one resonator to a different resonator. So sounds and lights are governed by very simple principles. One of the most fundamental ones is Lorentz reciprocity, which is root on time reversal symmetry. And this is easily illustrated by this picture. If you are in a concert hall and you can hear the orchestra, then this means that the orchestra can hear you back if you make a disturbing sound. This is reciprocity. And this is in particular very easy to break if you have a charged particle. And the way to do so is by putting this charged particle in a magnetic field. And this will break time reversal symmetry, meaning that if you now take this cyclotron orbit and reverse the velocity of the electron, you won't get the rewinded trajectory. For that, you need to also change the magnetic field. So there are limitations that time reversal symmetry imposes on states. And this can be shown very easily with just a 3-mode system like this one. We have 3 coupled harmonic oscillators. One of the eigenmodes will be this breathing mode. And there will be also states like this one where only 2 oscillators move. But what we cannot have is modes like this one, where the relative phases between motion of different oscillators are not either 0 or pi. In other words, if this mode exists, which you can see it propagates counterclockwise, there has to be a mode that propagates clockwise with the same energy. So time reversal symmetry forbids the existence of these modes with some handedness, which we dub as chiral in the following. Now, there are consequences in the many body of breaking time reversal symmetry. The first is the celebrated quantum Hall effect. If you have a magnetic field which permeates a 2D electron gas, the cyclotron orbits for the electrons will be closed inside the system in the bulk, but in the edges, they will be open. And this will create a channel for a conduction channel, which it's actually unidirectional and has a topological origin and was shown decades ago. There is an even simpler consequence of breaking time reversal symmetry, which is the Hexagonal bomb effect. If you have now a particle, a charged particle that can move from a point A to a point B in space, following either of these two paths, and these paths encloses a finite magnetic flux, but the particle is not feeling this flux because this is confined to a solenoid, then the wave function of this particle will acquire a geometrical phase, which over a closed path depends on the magnetic flux of the system. And this flux, this phase can be observed in interference measurements and is denoted in a Hexagonal bomb effect. Now, realizing breaking time reversal symmetry as easy as it is for charged particle is extremely hard, or very hard to do for something that doesn't have charge, such as a photon or a phonon. And also, if we try to do so through magnetoacoustic effects, this is very hard because these are very weak. So the way to do so, our approach consists of using explicit time reversal symmetry breaking. What you can get, you get when you use temporal modulations of the couplings between resonators. And this is exemplified by this seminal work from Sanhui Fan, where they show so for a photonic crystal that supports these two photonic bands that occur at different frequencies, a modulation in the dielectric constant allows for a creation of a sidebands of the lower frequency mode precisely at the frequency of the highest frequency mode, if this modulation frequency is tuned to the frequency difference between these modes. And in fewer words, this means that the effective Hamiltonian for this system will destroy photons in the lower sideband and create them in the higher. And this accompanied via a phase imprint, where you can also add to your modulation of the dielectric constant. And this phase is equivalent, completely equivalent to this phase that I mentioned earlier, the Hexagonal bomb effect. So this is an Hexagonal bomb effect for photons. Now we can do the same for phonons using optomechanics. And I don't need to introduce now what is optomechanics, but just to summarize, it focuses on the coupling between mechanical resonators through radiation pressure force. And if we modulate the number of photons in time, as I will show in the next slide, we can create effective interactions that resemble this Hexagonal bomb effect. And similar proposals to this one have been already used in optomechanics, for instance, in this macrotoroid resonator that supports two hybrid optical modes, well, a symmetric and antisymmetric optical mode, and a breathing mechanical mode. And by sending a control field here that is slightly detuned from the optical resonance, then a probe field at the optical frequency can create a beating that, if exactly matches the mechanical frequency, can make all the energy coming from through this channel to be dissipated in the resonator. And if you do this in a proper way and you play with the phases, you can build a circulator. So the energy of the photons will go from 1 to 2, from 2 to 3, and so on. So now I will describe how do we do this, not with photons, but now phonons. And the interaction that we exploit is the one that arises in an optomechanical system where it's in the band cavity limit, meaning that the optical losses are much quicker than the mechanical frequency, which in our case will be of the order of megahertz or so. Now, the optomechanical coupling, what it does is to create a periodic shift of the optical resonance. And if one now drives the system with the tuned laser, this the cavity will eventually wander or will be in resonance with this laser and will create a changing number of photons inside the cavity and a changing radiation pressure. And this, in this band cavity limit, gives rise to a change, an effective change in the spring constant of the mechanical modes. This is just for a single mode, and for the structures that we use, which are these nanobeams, this will just create this shift in the frequency. But now, if we now change the length of one of these oscillating beams, so the resonance frequency are now different, we can apply the same trick as earlier with photons, but now changing the number of photons in the cavity in time with precisely the frequency difference between these modes. And if you do so and work out the theory, which is relatively simple to do, it consists actually on assuming that the optical field will be in the steady state, since its evolution which is much quicker, then you get this effective interaction between the phononic modes living in one resonator and the other, with a phase imprint that it's externally imposed. And this is precisely now equivalent to the Hexagon effect. Now you can do the same as with photons. And this is hence caused by breaking of time reversal symmetry. The way this is implemented in the lab, well, this is done in this slice nanobeam structure, which resembled very much others discussed earlier. But now with this gap in the middle that supports a very tightly confined sub-wavelength, in fact, optical field, which is colocalized with this flexural, here I plot the fundamental flexural mechanical mode for this system, which is with Qs of order of 100. And this large colocalization between optics and mechanics allows for very large G nodes, which lead to a figure of merit of this effective coupling between these between different phononic modes of order of 10 kilohertz, which is larger than the intrinsic loss rates for this system, even at room temperature, which is about a few kilohertz, maybe 1 kilohertz or 2 kilohertz. The way this is done in the experiment, and I'm going to try to explain the whole thing, is well, this nanobeam is placed in a reflection setup where the drive laser, which enables the optomechanical interaction, is sent and reflected, and this together with a probe field, and this reflected signal is now mixed during in a lock-in amplifier with a local oscillator for which that oscillates at the frequency that is observed and allows to separate the resultant sidebands from noise. And since this reference now has a fixed phase, one can measure essentially the phase difference between a mode that is driven, let's say this one, and the mode that is arrived through the optomechanical coupling, let's say this one. And if you do that, you realize that the phases that are acquired can be tuned through the modulation phase that you imprint. And then this means that what we actually did with this is to create an effective and Hartog bond effect for these phonon modes. And we published this last year. Now, we would like to extend this protocol to larger systems, such as arrays, ideally. And one could do that by interfacing many of these nanomechanical or nano-optomechanical systems. But this is, in principle, tough to do in the experiment. And there is another idea, which is of synthetic dimensions, which, as fancy as it sounds, it just means that you realize that each of the mechanical resonators will support a higher order overtones, which at higher frequencies, of course, which can also interact through radiation pressure forces. And this you see in the optical spectra through all of these very nicely resolved peaks. Now, if you send modulations of the radiation pressure at the frequency difference between these modes, in principle, you can create an arbitrarily connected network, which of course is limited by the number of tones that you can supply and also the number of modes that you can observe. But with a single cavity, we typically observe 6 modes which can be interfaced. Now, the simplest case is the case of 3 modes. And with this case, something funny happens. Well, these are 3 modes where the modulations are sent at the frequency difference between each of each pair. And this is the simplest system which has a non-trivial flux here, meaning that the phase that you imprint on this link plus the phase that you imprint on this link plus this phase is actually equivalent to a synthetic flux, and is gauge independent. You cannot remove it by any gauge transformation, such as redefining the origin of time. And this is shown in the mechanical spectra now for one of the 3 modes as a function of this phase sum or this flux. Now you see that these lines that were originally degenerated do split as a consequence of the flux. And this is another proof of breaking of time reversal symmetry, which lifts this degeneracy. And well, it's in really good match with theory you can do for this. In this case, it's just a simple generalization of the theory above for 2 modes, but now it's a 3x3 Hamiltonian. And an interesting bit is that now the eigenstates of this system can be diagonalized in the momentum basis, and the phase differences between each of these eigenstates is log to 2 pi divided by 3. So it's actually not either 0 or pi, as I mentioned in the second slide. It's non-trivial, which is another proof of time reversal symmetry breaking. These phase differences we can also measure independently by means of correlations, which I won't show here due to the lack of time. But there is another thing that we can do here, which is driving one of the resonators and observing, these are experiments, by the way, and observing the evolution of the mechanical energies in time. And what you see here is that when you drive one, you will see these drive oscillations that go kind of evenly to resonator 2 and 3 if there is no flux. But as soon as you put a flux, a non-trivial flux, as you see here, of pi over 2, then you see that most of energy will go not to starting from mode 1 will go to mode 2 and 3 and so on, which is kind of this picture, but with nanomechanical resonators. And you can think of now taking these measurements. Now this is the horizontal axis is time and the vertical axis is flux, and you see that you drive now always the first resonator, but you see that the population is larger in the second resonator if the flux is pi over 2, and small if the flux is minus pi over 2. And the converse thing happens when you look at resonator 3. So you can, by changing the flux from plus pi/2 to minus pi/2, you can change the direction of propagation, the circulation of this in this chiral state. And in this, I have shown you the simplest example where we use frequency difference modulations to couple the modes. And what you get in the theory when you do this is a hopping Hamiltonian, which destroys sidebands or phonons at resonator 2 and creates them at resonator 1. But what you can also do it's to send modulations at the sum frequency. And if you do so and work at the theory, now what you get is this two phonon driving, called by some communities two mode squeezing terms. You can also create single mode squeezing terms by sending modulations at twice the frequency of the resonators. And you can make loops now like this one, where you replace two of the frequency difference modulation with some frequency modulation. And well, something happens already. If you look now at the spectra, now I didn't mention earlier, now I take the chance to mention this, the spectra for these resonators is only driven by thermal fluctuations. We just use thermal fluctuations to probe the resonators, all the eigenstates of the system, basically. And now if you do that with this loop, you see that the response for resonators 1 and 2 is flipped vertically with compared to the response of resonator 3. And this, of course, also you see other stuff like narrowing of the line widths in this region, where the modes are more localized. And this was a bit surprising, what we saw at the beginning. But here theory comes to the rescue. Now you can realize that this two phonon driving can be actually observed as a conversion. And how? Well, if you now think of, if you now split in particles and holes the coupling, now you see that for the plus frequency, what is actually happening is that you are destroying a B1, let's say, an annihilation operator, and creating a B2 dagger. So you are destroying a negative frequency sideband and creating a positive frequency. Sorry, the other way around. You are destroying a positive frequency sideband and creating a negative frequency sideband. Now, if you apply this idea here, you see that you actually have two loops that are disjoint. And the eigenstates, therefore, will be localized on particles and holes. And now you have to realize that the energies for holes will be reversed vertically with compared to particles. So basically, this explains this flipping now. Also, you can use now fluxes here to create chirality. And if you now consider a driven system where you drive resonator 1 and look at the energy of resonator 2, and do that in time and versus flux, you see that maximum transfer occurs where the flux is equal to pi/2. And when you drive resonator 1, when you drive resonator 2 and observe at resonator 1, the converse happens. So you can actually use the flux to amplify energy directionally in this system. And with that, I'm in my last slide. I hope I could show you that we can realize experimentally and explain theoretically an scalable network of nanomechanical resonators where we can orchestrate with optomechanical interactions with lasers, basically. We can create gain through parametric drives, 2 omega or some frequency drives. And we haven't talked so much about thermal fluctuations here, but we can actually use these chiral states to also move heat directionally, so to do chiral cooling, to say. And there is applications that we envision in networks of oscillators and sensors. I haven't shown that we can, using these parametric drives, we can both tune through fluxes the energies and the line widths of the system. And by doing so, we can do this type of stuff where we create something that is very interesting in non-Hermitian physics, non-Hermitian PT symmetry physics, which are the exceptional points in which both real and imaginary parts coalesce, but I don't have time to go into that. The outlook is we would like to now introduce more and more resonators and eventually, of course, realize lattices. And with that, I would like to finish and happy to take any of your questions. Here, this is the work that we are preparing to report these results, and these are the people involved. Thank you. Sorry, I cannot hear you.
Okay, thank you, Javier, for the nice presentation. I think that we have time for at least the final one, so we have time for 2 or 3 questions. We have the first one from Mohammad Bereihi. How do you couple to such cavities, both for the single device and the array platform? I think that you didn't explain.
Yeah, maybe I can go back to the slide where I introduce the coupling mechanism. Maybe it's here. So, so the idea is that when you now drive a single cavity with a detuned, strong laser, you can you can use radiation pressure to shift mechanical frequencies. So in a way, when you now coupled mods, you can couple now mods together by using different frequency resonators. And if you now send, you change now, you apply a force that is periodic in time with the frequency difference of these modes, you now will create a resonance so a sideband of one of the modes at the frequency of a target mode. So in other words, one mode will change the radiation pressure a bit. This will create a sideband, and you enhance this sideband using the modulation that you send, therefore enhancing the coupling to the other mode.
He means optical coupling. He's referring to optical coupling.
To optical, no, we don't have any optical coupling. We just have a single cavity. So it's just one cavity and many mechanical modes.
Okay. We have another question from Luis Martin Moreno from Zaragoza. So if you had a disordered waveguide, could you see weak anti-localization of acoustic waves when you switch the synthetic magnetic field on? Anti-localization. I
think that, well, that's the direction. Maybe I can go way forward to one of the supporting slides. This is I think this is part of a direction that we are pursuing. Now, of course, we could think of making larger lattices, and one particular case that sounds interesting is this one with 4 modes. And here you see you have 2 plaquettes, and if you now calculate the eigenstates of this, you see that you have one state that is really localized here, and you can change the localization of this state using flux. So in principle, we could do that. We just haven't done it, but yeah, it will be possible.
Okay, so let's go to the final question by Carlos Gonzalez. Thank you for the very nice talk. How strong is the 2-mode squeezing rate one can create as compared to the mechanical frequency? Is it enough to drive the system into a dynamical instability?
That's a really great question. Actually, well, I mentioned earlier that the couplings that we can get are of the order of 10 kilohertz of maximum, which is way, or at least even an order of magnitude larger than the intrinsic losses. The mechanism through which we induce the squeezing is the same. So we could have a squeezing amplitudes also of 10 kilohertz or so. And in fact, this is enough to drive the system above the parametric instability. This is what you are seeing here. This is a self-oscillating regime. This narrow peak is actually kind of a single pixel in the measurements. And this nonlinearity, it's kind of annoying for some of the experiments, because it saturates our system, it displaces the thresholds, and yes, but we can. Yeah.
Okay, so I think that it's time to close the session. So thank you, Javier, and thank you all the speakers of this session. So now it's time to close the whole workshop and to say goodbye. But before that, I would like to take the opportunity to thank the people who has made possible this workshop. First, most importantly, the Benasque team, the organizing team in Benasque, Tracy, Anna, Judith, and Iju, and of course David, who was in charge of all the technical aspects of this workshop. As always, they did a very fantastic job. Everything has gone very smoothly. Yesterday there were some problems with the poster session, but apparently they were due to the Zoom application, and it was not our fault. So thank you, the Benasque team, as always. Secondly, the speakers, we have to thank the speakers because they make the effort to prepare the talk and to give the talk. So I know from experience that is sometimes a bit frustrating to give a talk. So you give a talk and then the chairman says goodbye and that's all. So sometimes it's very frustrating. Of course, also for the people presenting the posters. I mean, I think that also they have made the effort to present the poster. Most of them are young researchers that, okay, this is not the real conference. I mean, to present a poster in this way. So it's very fair. So, and of course, the attendees of the conference, now we have around 60 people in the audience. So thank you for the attendance. I have been told that many of the talks have been recorded. So if you want to have a look, if you miss something from the talks and you want to revisit the talks, you can watch them in the webpage of the conference, so you can have a look to them. So, okay, so just to say goodbye, we have tried our best to mimic a real workshop and a conference, but it's clear that it's nothing to do with a real conference. So this is why we hope that in 2 years' time, we will organize a new workshop on quantum nanophotonics in Benasque, so we will enjoy the atmosphere and the three-dimensional versions of the researchers. So, but in the meantime, okay, stay safe and have a nice weekend. Okay, thank you.